Sir, YouTube is not working now. Is not working, sir. It is okay now.
Is it working now?
Yes, sir. Yes, sir. It is working.
There are comments coming no to me. YouTube link is not accessible. Like, let me see 1 minute.
Yes, sir. YouTube is not working. It is okay now.
Not working or now working?
Yes, sir. It is working now, sir.
Okay.
It's functional, full functional.
Okay, fine. Okay, now I am seeing. Yeah.
Welcome back, all the participants and the honorable members of the National Convention on Aerospace Engineering. We are going to begin with the technical talk to be presented by Srimati T.K. Anuradha for the Dr. Vikram Sarabhai Memorial Lecture and Felicitation. And in the continuation of the same, I would request our executive member of the Kanpur Local Center, Ms. Kushnuma Parveen, to read the citation of Dr. Vikram Sarabhai. Mr. Parveen, Ms. Parveen.
Good morning to all of you. First of all, I would like to thank you to each and every person being here for the 34th National Convention of Aerospace Engineering. And it's my great pleasure to read the citation of Dr. Vikram Sarabhai. Dr. Vikram Sarabhai was not only an imaginative and creative scientist, but also a pioneer industrialist and institute planner. He made significant contribution in the field of cosmic ray physics and in the development of nuclear power and space programs. He took up the nuclear programs with a challenge and added fresh dimension to the space research program in 1966 when he became the chairman of the Atomic Energy Commission. Dr. Sarabhai was born on August 12, 1919 at Ahmedabad in a rich industrialist family. His early education was in a private school and Gujarat College at Ahmedabad. He then went to Cambridge, England, and from St. John College, obtained his tripos in 1939. He came back to India and started research work in the field of cosmic rays with Sir C.V. Raman at the Indian Institute of Science, Bangalore in 1945. He went back to Cambridge to carry out further research on cosmic ray and there in 1947 obtained PhD degree. It was early in 1942, Dr. Sarabhai conceived the idea of starting the physical research laboratory in Ahmedabad. Soon after his return from Cambridge in 1947, Sarabhai started looking for a place for this project. He got a few rooms at the MG Science Institute to start the laboratory, and the laboratory was formally opened in April 1954. Dr. Sarabhai made the physical research laboratory virtually the cradle of the Indian space program. Dr. Sarabhai not only encourages science, but also devoted a good deal of time to industry. For over 15 years, he nurtured a pharmaceutical industry. Dr. Sarabhai helped to build the Ahmedabad Textile Industry Research Association in 1947. During 1949 to 56, he remained an honorary director of ATIRA. In 1962, he helped to found the Indian Institute of Management at Ahmedabad, and during 1962 to 65, he remained an honorary director of this institute. Today, the success of the space program in our country is largely owing to the groundwork prepared by him in this regard. Due to his effort only, India could launch its first satellite, Aryabhat, just 3.5 years after his death. Dr. Sarabhai was a world-renowned figure in the field of space research. He was awarded Bhatnagar Memorial Award for Physics in 1962, Padam Bhushan in 1966, and Padam Vibhushan. He was elected in the Vice President and Chairman of the UN Conference on Peaceful Uses of Outer Space in 1968. He also president over the 14th General Conference of the International Atomic Energy Agency. Dr. Sarabhai died on December 1997 at the age of 52 when he was at the peak of his achievement. In memory of his dedicated service, the Institution of Engineers India Institute an annual memorial lecture in his name during the National Convention of Aerospace Engineers. Now I would request to Srimati T.K. Anuradha ma'am to kindly deliver Dr. Vikram Sarabhai Memorial Lecture. Thank you so much.
Thank you so much. It's, again, I would like to tell from the bottom of my heart that it's an honor for me to be delivering this prestigious Dr. Vikram Sarabhai Memorial Lecture today at Institute of Engineers. In fact, it is such a blessing too, for I am from Indian Space Research Organization, where he has been the father of Indian space program. So today I would like to take you through the evolution of satellite-based communication in India. So while I'm doing, I would like to take you through a brief background of how we started and what were the various phases we passed through and what are our assets today and what we plan to do in future and what is required of all of you, the younger generation who are listening here, how you can contribute in the future. So morning we heard about the beginning of space era. In fact, it is very interesting to know that the World War II, which ended, it also brought the dreams of humankind for the physical access to the space. That gave a shape. Why? Because of the infamous V2 rocket from Germany, which created havoc on several countries during the war. After the end of the war, von Braun, the V2 maker, he was gained by United States of America. The V2 manufacturing facilities came under the then United USSR, Soviet Republic countries who had joined together to form USSR. Centuries of knowledge of astronomy was already there, but there was no access. Today morning session, Chief Guest Shri Kiran Kumar told how the space was one of the last one to be accessed after the land, the water, and the sky is just above us. Then we have the space deeper into the sky. So it could shake hands with this rocket technology. There was a means now to have a physical access to space. When we say space, literally, it means anything above the Karman line, a imaginary line, Karman line, where 110 kilometers above the Earth. So beyond that, we will technically define it as space. So going there was possible with these rockets to understand better. So it was very soon after the World War was over, these technologies got developed, and 1957, there was already a man-made object which went into space, and it pushed the frontiers of space science and technology in fairly a short span of time, with a fierce competition going on between the giant superpowers. And it got followed by a few more nations from Europe. Moon was accessible. People could land on moon, and solar system planets were accessible. We could send the instruments. Humanity could send the instruments. They not only entered the space, but imagine landing on the moon. Marvelous achievement indeed for those days, and all happening in very short span of time. So what was happening in India when all these wonderful things in science and technology and the space, the final frontier was opening up? Where were we? India had our own post-independence challenges, and we had unhealed wounds of partition. And still, there were certain states which had to be integrated into India as a nation. We had wars with neighbors, economy was in doldrums, and even there was a shortage of food. We had to import it. There were several social disabilities. But India always has a strength in it. It emerged stronger and stronger with stupendous efforts and its visionary leaders. A leader among South Asian country today, jubilant with green, white, blue, and brown revolutions. You are aware of that. India became very, we were able to export food shortly with the green revolution, made the dairy products made available, the ocean products, it took a great leaps, and the brown revolution, the oil products and other crops. Along with that, it was also a thrust in science and technology. The then leaders very nicely understood that it was science and technology which can take the young, independent India forward. Today, modern India is poised to seek permanent seat at United Nations, and it has emerged as a spacefaring nation among the handful who can do end-to-end space-based activities. It was only a couple of years after Sputnik was launched, and here, just 1957, the launches happened, and just we have not around 1960, and there were ideas that why don't we start the space program in India? Is it possible, the conditions, what I told at that point of time? Many question naturally the relevance of this space program in India. We don't even have food. We have to import food. What are you talking about? Do we even have the hands on the technology required? Are we able to do that? It's all for the rich nations. It is a fancy game for them. And they are playing, they want to go to moon and they want to go to Venus or Mars. And what is the use for us? Many ask such question, understandingly. But it was a brilliance of the vision by the father of Indian space program, Vikram Sarabhai, who could convince that we shall not run any race with these giants. That's not our idea. That should not be our aim at all. Whereas, let us not leave out any opportunity to bring the advanced technology in the form of space technology, which is getting developed for the betterment of the society. And we keep advancing our own indigenous technology too, side by side. It was a brilliant strategy. Who could deny it? This initiated the space program in India under the aegis of atomic energy as INCOSPAR, Indian Committee for the Space Research. It took birth in 1962. So it was the two stalwarts, Homijay Baba, who was there heading the chair of DIE, and Sarabhai, who brought in unprecedented alliances, strategies, and with exemplary diplomacy within and outside India. Just imagine, it's not easy for starting a program which is so ambitious in the country, which has many priority problems. You need a lot of strategic movement, and you need a lot of diplomacy within Indian policy makers and who have to finance the program. And you had to bring the alliances very judiciously. Why? Because we did not have the technology. So there it goes with that kind of synergy and innovative ideas. Very soon there was TERS, Tumba Equatorial Rocket Launching Station, in 1962. With the help of USA and France, the setup was made. And very soon it was, there were sounding rockets from Russia, from European countries, France and USA. I know those who were in fact the Cold War was going on two opposite ends. This was a platform where they could come together and start the activity. What can you say about this diplomacy and alliance, which were very intelligently brought in? Very soon, we had our own indigenous sounding rocket in 1965. I keep telling the years because you have to understand that how quickly and how wonderfully India moved in those lines. And that was also the time this TERS was dedicated to United Nations, opening up for anybody who wants to do the atmospheric research, putting the sounding rockets, they can come here. So India started making the eyes of everybody around the globe to look at India and what are these people doing. And so much of futuristic thinking that even when we are doing one step, at the same time, think of what is going to happen after 7 to 8 years, 10 years ahead. There were ground stations which were brought in, experimental ground station in Ahmedabad for television, and in RV, RV, a place near in Maharashtra, wherein the ground station was brought. It was a story by itself that there was a proposition that we can get 1 year a free satellite available to us for all their experimentation, but we can use it for whatever we want. And at that time, by US, that ATS-6 satellite. And at that time, Brazil was also in the race to get this satellite for their own advancement of the space program. But because we had the ground stations made ready well in advance, and there it was, and India got the opportunity to make it happen. What a feat indeed. And, the TV experimental broadcasts and where Indian community was not even aware of it. And today it's all a history. And the vision has been made into reality. I just want to put in one chart how well the programs were defined. Very much useful for the common man, the communication, remote sensing, and weather, meteorology. Related satellite programs were very much defined. And then at the same time, when we are going ahead with that, we had to bring in our own access to space through Indian launches, and the programs were defined. But applications always first for us. And then later on, we had the navigation program added. During all this, the scientists inside the heart, they never died. They always wanted to do explorations and scientific programs. They were also going on with whatever meager budgets they had for this purpose, because the main focus was bringing applications, the technological applications to the common man. So today, as you see in this chart, and any field, if you see, we have state-of-the-art technology. And what has happened is India stands self-reliant in the space programs. I keep insisting on the word self-reliant because it is not self-sufficiency. Nobody today in the world is self-sufficient. We have to be self-reliant. We have to earn that international respect, and we have to earn that platform where we are equal in terms with them so that we can have a give and take. Today, India stands having launched 342 satellites from other countries. Whereas there was a time when we had to go behind for a very economic way of putting our own small satellites into the space. Today, 342 such satellites from other countries, even developed countries, are there, launched by India today. We had successful launches. Of course, we had our problems too, some unfortunate losses, and huge number of fleets of satellites in all these missions, as I explained just now, whether remote sensing, communication, meteorology, and later on added by navigation, have been launched. And in order to encourage the younger generation, the students are also helped out to put their hands on so that they get the experience and come join to do bigger jobs. In all that, it's also very interesting to note that India built two very advanced communication satellites for the European establishments in the first decade of this century. 2001 to 2010, we could do that in the first decade of this century. So it was one for the Eutelsat and one for the Avanti. And it was a great experience in understanding the international way of making the things happen. And it also showed the confidence the others have in us. So this is one of the very important thing the youth has to look at it today. And now I'll come after this brief background to the SATCOM. How was it in line with the vision Vikram Sarabhai saw, or the vision of Indian space program, how it started, and how did SATCOM fit into it? Let us have how it evolved, the phase one. If you look at it, as I keep telling again and again, for us, it is bringing the technology to the common man and making it as usable applications. So if you look at that, even before we had any other technology available to us, we brought in the programs called satellite-based instrumental television experiment and the STEP program, the telecommunication experiment program. So these programs, we did not have the satellite. So, but notwithstanding, we were ready to take the satellites from outside the country who had made the satellites and make sure that the applications will start coming into the masses. Development of the society starts happening. In the process, learn what we have to do. Prepare yourself. Put the grounds ready for your next step. So in this process, the site experiment was hailed as one of the most successful sociological experiment. 2,400 villages on the experimental basis in 20 districts. They were having the broadcast, and nearly 50,000 teachers were trained as science teachers at that time using this program. It was a great success. And the ground infrastructure, what is required for such broadcast systems all over India, started taking a shape. Very soon, as a sequel to this site, we had the STEP program with, again, a foreign satellite. It was a Franco-German satellite symphony. And in this, our Indian postal and telegraph also got involved, and how we can communicate from one corner of India to other corner of India so quickly, efficiently, it was demonstrated. And these two satellites, they really helped us to set a foundation, not satellites, a program for the ground system designs and installation, operation, maintenance, how to do it, because it's a long-term activity which we had to learn, and for the future, our own satellite programs. And then, meanwhile, the second step was, now we are ready on the ground, we need the satellites, big satellites. So these satellites, we ordered and we got it from outside, paying money, with a contract such that we also participate in the build of the satellite and they help us to learn. And in this process, the INSAT-1 series of satellites, they came into operations. Of course, we had certain setbacks. There was something very unique on INSAT-1 series of satellites, which continued even today. We wanted satellites not only for broadcasting, not only for communication, but we want to add these things together on a common platform. Why? We could not afford to keep putting one satellite for broadcast, one for communication, and one for meteorology. At that point of time, it was important we effectively use the resources, and these were our design specifications for INSAT-1, and it happened. And once this was done, it became a pre-runner for the Indian communication satellites, which we could build. And that was demonstrated. Again, we cannot immediately build a big satellite. That was again demonstrated by Ariane Passenger Payload Experiment. Look at the name, Ariane Passenger Payload Experiment. Ariane was launching its one series of rocket, series 4. At that time, they were ready to take a free ride for any satellites who were ready to put, because they wanted to establish their first launch. And India dared, again, we will make a satellite. And for the first time, 3-axis stabilized satellite was put on that rocket, and the rocket was a success story. And we learned a lot in making such 3-axis stabilized satellites, what was required, and how to have communication from the geosynchronous orbit or ground systems. It was a wonderful step indeed. And in all this, even when we were INSAT ones were coming into picture, next step, think ahead always. So the moment it happened, by 1977, by these times the satellites became operative, etc., we had INSAT Coordination Committee. How are we going to use it? It's not that one department, I put a satellite and everybody clap hands and go, no. It has to reach the common man. It is possible through the concerned departments. So there it was, International Coordination Committee with Department of Space, which was already formed, and the Department of Telecommunication, Meteorological Department, Doordarshan, and All India Radio. These were the primary members of this committee who were the immediate beneficiaries of this program. Further, many other departments joined. This committee got renovated. The way it got joined, Science and Technology, Ministry of Defense, Ministry of Information and Broadcasting, and Department of Information Technology, so many of them, including Finance Department, Regulatory Department. What does that show? It shows the importance of joining hands with all concerned and taking it for the final goal. It is not a personal glory or one department's glory. It was meant for bringing applications to the common man. The joining of these departments and utilizing these capabilities was something remarkable indeed. Then we went into the phase 2. Phase 2 was, we had all these users who were introduced about satellites, how to use it, and having given that, initiated them, they started becoming tough customers. They wanted more and more and more. There was a huge need for satellite. Everybody wanted to have channels on the broadcasting, and there was DTH applications which started. So many DTH operators, and the business went in a big way using the telecommunication. So many applications just bloomed. And the moment it happened, and we had to bring in the capacity building to meet these user demands with in-house satellites, like INSAT 2 series, 3, 4 series, and GSAT series, and various bands. This is something very important, as I tell you today, using S, extended C, C band, and Ku bands, all these kind of satellites, bringing in various kinds of applications. It was so important that India saw at that point of time the need for the spectrum and understanding how to get the spectrum. It can be another session altogether in the international level, how you can take it as a national asset, the spectrum. Unless you have your satellites, the spectrum is not yours, it's everybody's. Any number of satellites can be sitting over your country, and you may not be able to operate unless you have put efforts and you have done it. So India was successful in doing quite a lot of efforts in making use of this spectrum and bringing unique applications, like already VSATs were there. And as I told, the DTH started, and the teleports, where the cable TV systems, they would uplink and then give it to the cable operators, and they operate, and search and rescue, and data alert terminals, and data relay transponders for the meteorological purposes. And we had mobile satellite services, and we started hosting other payloads too, like navigation payload Gagan on these INSATs and GSATs, which are going on the geosynchronous orbit. In this whole process of building, what happened? it was a beautiful synergy within the country. There was a lot of indigenization of parts, processes, materials and systems and infrastructure. Today, what you see as a space infrastructure, which has happened over this process, this synergy process, it went on. We have wonderful launch pads and wonderful satellite test facilities, satellite building facilities, rocket building facilities, our own liquid propulsions and solid propulsion systems, and how we are able to do all those things. And it was not possible with the ISRO employees. It would not have happened. It was a huge participation of public and private sectors, even from those days, even from the early 2000 or little prior to that also, it had started. There was a lot of training, skill set development, and in fact, there was a funding programs so that we get help from public and private sectors. Today, HAL as a public sector is one of our major partner, giving us, the structure for every satellite and the rocket stages, and satellite for launch, and the Indian soils too had to be done. As I told, after bringing the applications, we had to look for more self-reliance. We had to launch our own satellites from our own rockets. So there were satellites which were built on those rockets at that time, which were coming up. And in fact, we had a beautiful example of even our workhorse PSLV, which could take a communication satellite, which can go into reach the geo orbit through the mission operations, etc. So these kind of self-reliant programs, indigenization, participation of the entire country in building the satellites and bringing applications went on. And as I already told, we also built satellites for the foreigners. Looking at our capability, they had the faith we could bid for it and we could get the contract to build the satellite for them. So, but there was a humongous growth of capacity demand for the satellites. And it was not possible that ISRO is making so many satellites that everything is met only by Indian satellites. It was not happening. Then we had to bring in very effective SATCOM policy, guidelines and norms, so that we can make use of the foreign satellites too in a systematic manner, in a judicious manner, so that Indian users are not affected. They're not left in the lurch. No one should say, I don't have capacity and I could not have my business. That was not right. So a beautiful program policy was brought in. At the same time, we had to protect the Indian development of engineering skills and the technology skills in the space industry. If you start buying everything ready-made, your own growth will be curtailed. For sure. Morning also, I was trying to tell the same thing. Today, everything is opened up, but we have to make sure the generations now who are taking that we keep growing in our homegrown skills. We have to keep improving that and improvising that. So this National SATCOM Policy Framework was there well in time, and it helped to give the capacities judiciously, so that and you can prioritize the national needs where we have to use, and pragmatic way of hiring and protecting the Indian assets. As I explained, it went on in a very beautiful manner indeed. Then came phase 3. The phase 3 was when we had to go for more advancements. Building advanced technologies elsewhere in the world, it was happening. So the phase 3 got initiated almost 10 years before what we are seeing today. The work started on it. And when we started working on it, the first great thing that we brought in was the new class of fixed satellite services through what are known as high throughput satellites. So the technique here is basically to split the spectrum available, which is always in shortage, into small beams with large power, and reuse that frequency, so that in effect you are virtually enhancing the bandwidth and satisfying various requirements. Based on this reuse, typically the throughput can be enhanced multiple times. For example, if you see GSAT 11, what we have done, whatever that 125 megahertz per beam we thought of, there are 32 beams you can see. There were, and each spectrum chunk is divided into 4 portions. Of course, polarization gives 2 portions. And also it is further split into 4 portions so that they won't be side by side. If they're side by side, you have interferences. So for example, if you take the yellow, you can keep reusing it, correct? So if you keep reusing this, that means the same frequency is effectively used. Because it is a narrow beam, you can pump in more power into it. And in effect, we have done a 16 Gbps satellite using 500 megahertz, what was available with us. So this is the throughput which you can achieve. As an example, I'm trying to give. And we never bring in anything just like that because we have to learn and do that. It is highly complex. It is a multi-beam system which needs very special antenna, huge antennas with RF tracking system, because if you don't track these small beams, what you want to put on Kanpur, it will be somewhere on Sri Lanka because the distances are so high, and multi-port amplifiers, high power RF systems, because we are increasing the power of the beams so that the power requirement on the satellite is increasing. It means huge solar panels, take anything, huge batteries, and how to support these large antennas which need to even rotate, So you need such special structures and 15 to 20 kilowatt of power generation. In all that, satellites are also humongous. They are 6 to 10 tons of satellites which can carry these kind of things. So India could do it. And before that, we did GSAT 19 for a demonstration with 1/4 the capacity. At the same time, we used it to put it on our own rocket, Mark 3 rocket, so that we are also bringing in some service, getting hands-on experience, and we have a payload for the rocket. And in the next Mark 3, we put GSAT 29 along with our KU band, which we already had good hands-on experience, the Ka band also, and steerable beams. And in addition to that, we put wonderful experiments on that, like QV band, futuristic thinking, optical band, how we can put that, and also from the geostationary orbit, how we can have high resolution camera. These kind of experiments were all loaded into it, and it was also successfully launched by Mark 3. And this is one part of the advanced technology. There are many more, as I'm showing you here. For example, I already told you higher bandwidths are available as you go higher and higher. For example, whatever 1 gigahertz of bandwidth available for us in KU, it becomes 8 gigahertz in Ka, so that you can have more applications, more data transfers, and QV goes much higher, multiple times in optical bands. They are in, terabits per second kind of throughputs. So higher bandwidths have to be made use of because there is a spectrum crunch. Everybody cannot be using the same spectrum in the same area. There will be a total chaos. It is not possible. So the technical solution is to keep going for higher bands. And that brings in a lot of challenges like atmospheric absorption. These bands, when they pass through, hardly they reach the ground. So how do you do that? You have to bring in some kind of, intelligence and advanced modulation and coding, improved roll-offs, and you make it very efficient with protocols. All these kind of technologies go into that. And at the same time, as you go higher, we also need more flexible satellites, which can have dynamic power allocation, spectrum allocation, and coverage. It is not easy, as I'm telling you today in this lecture, because everything is so involved and specialized field by itself, and it needs enormous amount of activity which goes behind that. And we have to bring in security for the communication. Today, everybody's buzzword is, quantum key distribution and quantum communication. You have been hearing about it. So we also put we made an experiment recently, you might have heard. Space Application Center has done a demonstration, albeit in a very preliminary stage. We could show how to do the quantum key distribution. You have to get the hands-on experience. So these things are going on. And in all that, satellite is becoming bulkier and bulkier. We have to make it small. Otherwise, the launch cost goes up. So we had to bring in new kind of propulsion systems. Any satellite, 60 to 65% is propulsion, what we carry. Because after the rocket leaves it in a particular orbit, elliptical orbit, we have to keep firing that small motor using our own propulsion on the satellite and go to the 36,000 kilometers. So it is a huge amount of propulsion which becomes waste once you go into the orbit. It's all used up. So now the thing is electric propulsion systems, which in fact, there were some, when I was program director, we made certain calculations that if you are to put the same payload like GSAT-11 and whose liftoff mass was 6 tons nearly, using all electric propulsion system, it can become around 3,000 to 3,500 kg, and we can put on our own Mark III rockets. Right. So this kind of, win-win situation, satellite becomes sleeker and we can put on our own rocket. It becomes less expensive. And then who is going to enjoy that less expense? The cost per bit reduces for the users. These kind of technologies have, are in different stages of experiments, realization, demonstrations. And this is the phase 3, which went on, and quite a lot of has been demonstrated very, very effectively, in fact. And so we did all that. What happened? We have, what is the resource finally we built for ISRO? If you just look at this timeline, the way the satellites have increased. I'm just putting only the communication satellites. Equally, the satellites have increased in remote sensing area, and we have also done wonderful things in meteorology and hosting the payloads on these, also on these satellites, and our own low Earth orbit meteorological satellites. And we have scientific programs which went, navigation program, Indian navigation program. With all those things, look at the communication satellites which are gone and the technologies also which are being reached. This is the evolution that has taken place in leaps and bounds. All these satellites are not useful today in the orbit. You can see nearly more than 40 satellites, which you can see from 1980 to 2020. No, because they have limited life and they have to be replenished. Today, communication satellites, we have 17 communication satellites. And with that conventional, what I told, not the high throughput, we have conventional, we have 300 transponders, and we have 25 gigabits of data, which are the space segment resource for us today. And on these satellites, we have hosted, as I already told, Gagan payload and other useful payloads, which I'll explain very shortly again. So this is our asset in the sky. So what we built all this, what did we do? Did the vision become reality? The visions got converted into missions. We have so many satellites programs. But bringing the application to the common man, did it happen? Look at this for commerce and business, which is important for the growth of any country. Many closed user groups, ATMs, be in Timbuktu, and you can draw money from your bank anywhere. And the digital news gathering systems, mobile platforms, stock exchanges are today so much dependent on the satellite links and the e-governance. How many of you are aware today, including things like, it has been made so digitized, and it is possible that the government at Delhi and a smallest form of government, a panchayat, which is sitting in a village, they have to be easily connected. That is when everybody can progress together. It has happened today because of this kind of very small aperture terminal we call as VSAT technology. With the VSAT technology, today we are able to do a lot of communication applications which are going on today. And not only in the commerce and distress, we will have, India is prone to many kinds of distresses, be it cyclones. We have a long coastline, and 70% of the coastline is, prone to cyclone effects. One is coming already, even today when we read the news, and earthquakes and, even havocs, rain havocs and landslides, or even desertification. Suddenly there is lack of rains, and these kind of things are very essential using the communication. How are we able to stop these disasters? No, you cannot stop. But which are mounted on these satellites keep gathering the information, and when we keep gathering this information, it becomes a database, and there are a lot of programs developed, prediction algorithms, etc. And ISRO also is part of those things with the Met department. And when we bring out these things, you have the mapping of the flood areas, drought areas, all these kind of things. And when it actually happens, when the distress happens, none of the landlines will be reliable, because you might have lost it. It's only the satellite links which come into picture, so that the moment it happens, the reliefs go in time, the rehabilitation takes place efficiently, and how to do the mitigation of whatever losses have happened. And again, it goes into the database, and your preparedness increases. In this way today, any cyclone hitting, you hardly hear huge life loss and all is not happening. There is enough early information and protection of the people that goes on. And our communication satellites have played a big role in that. And another important thing is there is international search and rescue program, international. As you see in the global map here, India is also part of it. It is satellite-aided search and rescue, in which there are very standard protocols, standard frequencies, and these people carry a SAR terminal, whether it is in the air or the ship or hiking anywhere, and they have the navigation tools also along with them. And if there is a distress, they just have to push the button, or sometimes they don't even have to push. For example, if there is a sudden landing, sudden change in the velocity, the water touches it, this will automatically generate the signals, and there is a help which will immediately arrive and save the people. Looking at this, we thought our small fishermen also need such things, because these things are put on big ships, these kind of terminals. So we brought our own scheme called data alert terminals, and ISRO developed these terminals and handed over thousands of them to the coastal areas. And today, just like as I was telling for the weather reading, we have the data relay transponders all over, and they will be sending, automatic weather reports to the satellite. It accumulates, sends it to the meteorological department, which work is going on. The same concept, give a similar terminal to our fishermen, and we also tell them if it is the distress one, you press one, varieties, whether it is, whether he's drowning or etc. And also it got fitted with a new generation of terminals with the NAVIC messaging, so that they receive back. The hub will send it back to NAVIC, and NAVIC will transmit it back with the coordinates, and the fisherman gets information. And there are also methods that today fishermen do not cross the international boundary lines, because their position is very well known, and they keep getting the alerts and this kind of applications. Why I'm telling is, these are the technologies which have gone into grassroots, going to the common people, and who don't even know what is technology or what is satellite, but they are making use of such technologies today. And mobile satellite services is in a big way. And if you see that beautiful satellite, it's the Indian satellite with a S-band antenna, which can open like an umbrella, a great technology. And it was so complex, and we were successful in having this technology. And this satellite can provide, two-way communication. And similar two-way communication is also there for, chartered users with their own satellites we have made for them. At the same time, we have these kind of availability for various kind of terminals are also made. And today, whether, as I told, a real-time train monitoring system, what we have that is being used. And we also have for the fishermen this application so that they can have two-way communication using this also, not common fishermen, for the bigger boats, etc. So this has come as another innovative service which we have provided there. And what can I say about the broadcast? I mean, this is something, the bread and butter of the communication industry, infotainment. Today, if anybody is interested in making money, it will be the broadcast and the telecommunication for the business purposes. So there are other common man applications which it may not be money making for them, business people, but absolutely essential, which ISRO will keep on providing. So this is a huge business today, and India with its population always has an advantage in these kind of business. Nearly 197 million TV households are there in India, many with teleports. That's why 60% of C-band capacity is being used for the television purpose, using teleports. And we being such a vernacular country, so many languages, everybody wants to have their own regional programs. And how many DTH channels? I think 800 to 900 DTH channels are there in vernacular languages. Choose a big bouquet, whatever you want. And the operators are also many, and the capacity is not at all sufficient from India, especially in the DTH case. I think nearly half of it is taken from the foreign satellites, as I told, with our SATCOM policies, the way we have done. With our new technology of high throughput satellite, what we have done. Today, India has ISRO has become a partner in powering the Digital India program. So there is a huge program which has got a thrust by Government of India, wonderful program connecting every nook and corner and every village, give the broadband to them and they get connected. You know, in olden days, we used to tell that once a road is laid to a place, that place will develop in its business, etc. Today, what replaces that road is broadband. So if you have the broadband, the business opportunities and growth, economic growth, etc., it's all a study which has been made. So today, Indian high throughput satellites are joining hands in hands with the terrestrial optical fiber links which are being laid, because they cannot be laid everywhere, right? So we have difficult terrains and we have our islands which are physically separated, and we need to connect them, and nearly 6,500 gram panchayats are connected. And not only that, many business people have come up asking for the capacity from these satellites also for business applications. And when we are talking about the societal needs, the most important is health, which reaches every corner. Telemedicine is one successful story which has happened. And today, what numbers you are seeing, the hospitals, mobile nodes, super special, they were multiple numbers, 3 times, 4 times more when telemedicine programs started. Today, though the need has increased, need has not reduced. Though the need has increased, today it is augmented with terrestrial systems too. Along with that, it is essential that satellite provides the telemedicine for certain terrains where the terrestrial links cannot happen. Even with that, these are the numbers what we have. And, a semi-expert in an area, he can take the samples and then consult the big hospitals, and the villagers don't have to move from their tiny villages to the big cities just for any small complaints also. And they will know if it is small or large also through these kind of things. And most importantly, our own defense teams, which are there in the difficult glacier areas, they are able to get this help, which was wonderful. In fact, we had a serious, tele-education is my next slide. We had a serious thought, do we really need these programs, or can we use this spectrum for something else, useful thing? So because a lot of, networks are available today, 5G and terrestrial networks and all. But we called all the state representatives and discussed with them. I was touched. I was there on the chair and I was really touched that the way it came out, that how effectively it is being used for the underprivileged people at, at very low cost. And they all told, please do not stop. Whoever has higher, let them do, and we don't have to have them, but you cannot stop these programs. India is a country where, we live in different ages. We need all kinds of technologies. So this was wonderful. And telemedicine, especially when the integrated defense people came and told us that how it is helping them. They are in very difficult terrains and they cannot bring everybody slightly unwell to the base camp. And this telemedicine has come in a big boon for them in such applications. As I told, tele-education already, the concept is very similar kind of networks and all that. And again, because India is having several languages and there is a huge increase in enrollment. Today, I read one report recently that the enrollment has increased so much. And for a change, we see that the gross enrollment rate is higher for girls even than for the boys. I mean, that's notwithstanding this, I just told incidentally. And that is the push for the education.
Because of that, in fact, when I'm joining, you're just showing your name, because that they have been given it, I think, with the same link.
Please mute your zone. It is obstructing the presentation, please.
All right. So I thought there was a problem. So we have acute shortage of qualified teachers and rapidly changing syllabi, which has to keep in touch with the time. And we have not only for those school children, we have professionals who have to keep on updating their knowledge. Today, unlike the earlier days, you don't have to go somewhere. Today, we are holding this wonderful conference on virtual mode. The tele-education provides, professors anywhere in the world. You can take them, or any professional experts. They can be talking to people who want to improve their professional knowledge, whether it is adults education in the villages, or the health education, or vocational trainings, which have to happen in every institution, and various training programs for the officers, etc. They are also extensively using it. This is from my experience. As I told, we had a talk with them whether we should continue with this program in the present modern other technological thing. Today morning, we heard about the fourth frontier from Shri Kiran Kumar. Space has emerged as, the fourth frontier after, the land and ocean and the skies. And defense is, as always important. Today, it is not just the SATCOM or just the, remote sensing or the navigation or the scientific data. All are required for every component of the defense, whether it is control, communication, competition, service. These are their standard 8 points of the defense. Everywhere, satellites and communication satellites too are playing a very, very vital role. You can imagine the importance of communication in defense and in deep seas, or you're in the skies. So this is another important integrated effort using all the fields. So did we touch the lives of the people? Did the vision become a reality? What are the factors for the quality life in any nation? We should have food and water security, environment, health, education. You should have security at the borders, managing the natural disasters. You should have growth in business and economy. And you should also have the entertainment and other related business. So tell me, which part of it satellites have not touched? And if you talk about SATCOM, of course, it is there in health, education, security, disasters, business, entertainment, and to some extent, even in environment and food and water programs, to a smaller thing, though it is taken up widely by our remote sensing satellites very efficiently. There have been many national programs which are continuously using. So this brings Sarabhai's vision to become reality till this stage. And these are nurtured by his visionary ideas and his programs, which he thought so much ahead One cannot imagine how he thought of that. He's a man who could convert his dreams into institutions, right? So having done all that, where do we stand? Version 2.0, we have to go. So today, the global trends, we are talking about geostationary satellite is too much crowded. No one more can go there. No, I don't want that place, but I can bring in a new technology. I can keep putting multiple number of satellites around the earth and then bring in the same broadband applications. I'll give much better thing, because as you are far away, your signal losses are more. Your signal has to travel more. Your latency is more. I'm going to overcome all that. And there are many, many companies who have come up. You have heard of OneWeb, SpaceX, Telesat, Amazon, take any of them. And each one is announcing, huge hundreds and thousands of satellites, and satellites in different orbits too. And there is an estimation that in 3 to 4 years, we'll be having around 35 to 40,000 satellites doing this job alone, other than our other regular low Earth orbit satellite, what they're doing. And, they are giving you wonderful advantages. You look at it, there is a global coverage. You're going all around. If you're at geosynchronous orbit, your high and very low, latitudes towards the poles are not covered, but you have a global coverage because satellites are going everywhere around. And they can use higher bands very easily because they're at a lower height and atmospheric effects are less on them. Of course, atmospheric effects are always there. And the users can use compact terminals because, the power is so much, you have not lost the signal. So you can use a compact signal. Also, higher bands need smaller antenna, etc. And there is a low latency. I can bring in new kind of applications like Internet of Things, IoT is another buzzword which is going on. So they are also claiming today that the experience will be very similar to as if you have a fiber connection to you. So this is the scenario with the LEO constellations. The LEO constellations also have challenges. The regulatory aspects are still being discussed at international level. So how will they coexist with the geosynchronous orbit? How will they coexist? Because as I told, in an area, the same spectrum cannot be using for the same application. It becomes very difficult. So there are certain norms which are being laid out, and even before the regulations have come in, the satellite programs have jumped in, and there are so many demonstrations which are going on today, especially countries which are affected. There are several countries, there are nearly 200 countries who are ready to take whoever offers anything. But not every country is like India. India is a country, we have our own technology, we have our own programs, and we have our own space asset, which we have developed over the years. We cannot just take it away. And India too has concerns, and a lot of technical solutions are coming out how to coexist. And the other big thing is the debris concern. We're talking about thousands and thousands of satellites. It is also, there is another report which says there can be around 1 lakh of these satellites around the globe. How is it going to work? Are we contaminating the space too after contaminating the earth sufficiently? These questions, ethical questions, legal questions are also there, and they're trying to address these issues. And of course, the scientists, the astronomers are having a real tough problem, especially in certain periods of time when they have to make the observation that there is RF contamination, and the satellites are twinkling like stars, and their observations are really getting corrupted. And every disruptive technology, when it comes, problems will be there, and technical solutions too will come out. Today, we are at a stage where problems are being alleviated, and we need to get the solution. In many cases, solutions are also coming out. And having so many satellites is not very easy, and you have made thousands of satellites. It needs hundreds of gateways. You need to be connecting, taking forward from one satellite to other satellite. And you need so many earth stations, in our town, what we have been using. And user equipments also become complex in their algorithms. Initial user equipments had to have a rotating antenna, but today they have come with better antenna that you don't have to physically move it, but the algorithms have to do the very complex computations. And these also have a challenge of meeting the broadcast requirement. Broadcast requirement means you send a signal and everyone gets at the same time. So by nature of the configuration, this is difficult, but maybe some solution will emerge. And maintenance is another big thing. These satellites are small satellites and near to the Earth's orbit, and there will be drags and pulls, and these satellites cannot live more than 3 years, 5 years, and as on today at least, whatever I tell is as on today. So you have to keep on replenishing them, and you need to keep maintaining, upgrading them, bring in the new things. Already we had seen this in GPS kind of configurations where it needs to be augmented continuously. It's a huge business. So many launches have to happen, even though hundreds of the satellites can be launched at a time. Those many launches are also additionally happening today. So if these LEO satellites are coming up, what is happening to geo satellites? Don't we need them? No, it's not true. Hundreds of satellites are functioning with long operational life, of course, and they have their own niche areas. Like broadcast needs are one thing, as I told, and disaster management needs continuous monitoring, and the geo is the best area, and reliable backup also for these LEO, is happening through our geosynchronous satellites. And if there is any lacuna or something, there is a sudden backup, even though there is a delay at that time, you can take it rather than not have the service. And they are providing, most importantly, the huge backhauls for terrestrial links. Today, it is being big pipes are being used with the geosynchronous satellites, and some more applications will definitely come up. And geosynchronous satellites are also going, as I already told you, I don't have to repeat it again, for smarter satellites, flexible, going for higher bands, etc., and using, make themselves leaner with electric propulsion systems so that cost is reduced, etc. And there are also many very futuristic ideas, and few of them have demonstrated also, like in-orbit servicing of the satellites. Like if some part goes wrong, the whole satellite need not have to go bad. You can have a quick repair there, or even you can do the refueling, which was also demonstrated. And today, geosatellites not only have to coexist with the LEO, they also have to coexist with many disruptive technologies like HAPS, higher altitude platform systems, or the terrestrial links, which are so much hungry for the spectrum, the 5G, and people are already talking about 6G, the interferences. So there is a huge need for very intensive studies on this, and we have very handful of people who have a total knowledge and who also are objective in their thinking, and not from the business point of view. These things have to be studied. These are urgently required. That is the scenario today, what is happening. But as I told, demands are ever increasing, and you can never satisfy the data demand on the globe, and demands will keep on increasing, and there will be a place for every technology. And especially, as I told, countries like India will live in different eras simultaneously. And as you see, you still see microwave towers some places probably, and you have the cellular links, optical fibers, you have the satellites. Everything is working to the high capacity, and we need more and more and more. So there is a need for a big business which can take up in this matter. So this is the way we are going. So can we live with the same policies what we had earlier is becoming very difficult, which was also envisaged nearly 8-10 years back itself. And a lot of thought processes went, and a lot of efforts happened in refining the policies. And today, I think it is in a good shape, and also at a good time that it is almost ready, and it needs formal approvals, etc. Final reviews are going on. And on one hand, the new disruptive technologies which have pushed it. On the other hand, India has paved the way for private ventures in space. So we need to have new policies, how to bring them in effectively, the private ventures too. And we need new norms and regulations which are going on. And National SATCOM policy to adopt for future is ready. You can call it as the second version of SATCOM in India, which is going to happen. And we are looking forward for that new SATCOM era to begin early with, synergy from all the ends. Thank you for your kind patience.
Thank you, ma'am, for a very exhaustive lecture that deserve really to dedicate to Vikram Sarabhai, an eminent scientist of our country. Now, I would like to request Professor A.K.S. Gangwar to introduce our I would like to request our headquarter, Mr. Sen, to felicitate our speaker, honorable speaker, Ma'am T.K. Anuradha. So kindly present the slide to felicitate T.K. Anuradha, ma'am. Yes, her felicitation is present here. So kindly have a look, because in physical mode, the Kanpur local center will send this registration to Honorable T.K. Anuradha, ma'am. I request her to please accept our feelings in the form of this citation.
Thank you so much. I'm really honored.
Thank you, ma'am. Now I would like to request Professor A.K.S. Gangwar to read the brief CV of Professor Devi Prasad Mishra, because Professor Mishra will talk in next lecture. So now over to Professor A.K.S. Gangwar to read the brief CV of Professor D.P. Mishra.
Thank you, Dr. Mukherjee, for inviting me. Good afternoon to all dignitaries and participants. It is time to read the citation of great professor of IIT, Dr. D.P. Mishra ji, and he is great technocrat, professor, and very spiritual person. And regarding his citation, Professor Devi Prasad Mishra ji is the present director of National Institute of Technical Teachers Training and Research, Kolkata. He has been actively involved in teaching in higher education for more than 25 years now. He held the prestigious position of former chair professor, Indian Oil Golden Jubilee Professional Chair, Indian Institute of Technology, Kanpur. He has a rich experience in research in combustion and propulsion field. He has been an active researcher in the field of ancient Indian education and ancient system of India. He believes in and propagates humanistic model of education. He has published more than 230 research papers in international and national journals. He has undertaken more than 30 research and consultancy projects from various agencies, research labs, and industries. He has developed 6 online courses under SWAYAM platform, a national initiative of Ministry of HRD. Besides this, he has designed and developed a unique new course, Introduction to Ancient Indian Technology, on SWAYAM platform. of NPTEL. He has published 3 edited books and developed 10 lectures in ancient Indian science and technology on Swayam Prabha portal. Over the last 10 years, he has developed several initiated lectures on ancient Indian science and technology and culture and tradition to more than 5.5 lakhs people across India to revive and reestablish ancient scientific and technological culture of India. He has also delivered several initiative talks on ancient Indian spiritual knowledge system organized by different organizations in India. As the director of NITTR Kolkata, he regularly interacts with the trainees of different online training programs and takes keen interest in improving the programs, even though his lectures and interactions with the trainees, he tries to infuse in them the ethos and spirit of humanistic model of education. As present, he is working in the area of developing a transparent feedback mechanism for the online training program being conducted by the NITTR Kolkata. At the national level, Professor Mishra has been the pioneer in leading mentor training program and initiative of MOE and AICT. Under his able leadership, NITTR Kolkata has conducted several mentor training programs for senior faculty members of different institutes of higher education across the nation. He has also published a few papers in engineering education system. So, with full respect, I invite Professor Mishra to deliver his talk.
Kumara, namaskar and vanakkam to all people and namaskaram to all the participants. And after listening to Madam Anuradha about the penetration of the satellite and systems and space technologies into the arenas of life of all people in this country, I feel that it is now a part and parcel of the human life. And I was thinking as if it is like a Brahman. Isavasya midam sarvam jat kinchit jagatya jagat. That means entire things are being now being what you call part and parcel of the things. It looks to me like that. And what after listening to him, I am really thinking what I will talk. But let me give you a little different perspective or the aspect particularly not related to aerospace, space aspect, but the maybe aeronautical aspect. And if you look at before that, I would like to also explain the sloka, what I recited in the beginning, that Om Shana Bhavatu Shano Bhunaktu Sha Viryam Karavave Tejo Sina Vaditam Astu Mahabhidveshave. That means I'll just tell you, explain the things because people may not be aware. We are living in a modern era, so we do not know a lot of things as I have interacted with various people. That means we'll have to live together, we'll have to eat together. Of course, we cannot because on the virtual mode, and we have to also tolerate each other. And also, we should not have na vidvesava means enmity among us between the teacher and the taught. It is like an interaction program. So if you look at today, nobody can escape the power which is being prevailing over the life of the not only the Indians but the across the globe, because the technology plays a very important role, and we cannot escape it. We cannot also leave it, even if we do not want to, because the technology has really created havoc, and also it has changed the mindset of the people. So let us look at what is the future perspective of aerospace technology for modern India. And when you talk about India, it is a very great country having a great civilization. But today we are at the crossroads. So also the aerospace engineering. So also the aerospace program of the India. And if you look at that, we are having aerospace for the defense related things, like we are having various kinds of missiles we have developed because we'll have to safeguard our country. At the same time, we'll have to have several host of the things what we are doing as Madam Anuradha has already touched upon. I will not get into that. But we are having very ambitious programs like what you call hypersonic technology, like scramjet engines. Both the ISRO and the DRDO are working on that, and they have already demonstrated to some extent. And also we are having a big program of Chandrayana, and then our unmanned aircraft vehicle programs, which is very neat for these things. So keeping in mind that if you look at who are the drivers of the aerospace technology in this country, and the major one, if you look at, is the ISRO. So far the space is concerned, and talks about the rockets, spacecraft, satellites, space probes, landers, rovers, and several host of the things. And it is touching upon all the lives of the people, from the very downtrodden to the very rich people. Of course, the business is coming because of that, and also some other regions, but that is one of them. And DRDO is basically about the combat aircraft, transport aircraft, missiles, helicopter, UAV, national, NAL, National Aerospace Laboratories, which are dealing with the basically aircraft manufacturing, assembly, design line, aeronautical agencies for LCA, light combat aircrafts, Hindustan Aeronautical Limited, like CMD today was there, and is about the production of the engines, components, and helicopters. And now it has been with the ISRO is trying to get into the space program as well. And there are several academic institutes, academia are involved. Of course, the topmost is the ISC, IITs, and NITs, and several other institutes are doing. If you look at the major clients, if you look that way, basically it is the armed forces, so far the defense is concerned. And it's also civilian aviation, if you look at, and of course the other aspect, education, all the aspects, facets of the things are there. Therefore, I have not really jotted down here. If you look at the India's ballistic missiles is having all the programs which can go for something 5,000 kilometers range. We are having the capability to deterrent kind of things that we are having. It's a very ambitious program, and we are doing well. If you look at ISRO's is really doing marvelous thing. We are having SLV, ASLV, PSLV, GSLV, and GSLV Mark III, and that we are having a very ambitious programs of the sending the human beings to the space, because today a lot of companies are also trying to send, as Kiran Kumar told, that the frontier is the fourth frontier which is to be owned. But I'm afraid that we have already owned land and what you call air and water. Then what will happen to the life? Similarly, there also will land, because our scriptures, our tradition says that we need not win over anybody. You'll have to win over upon you. So, and that is the things where the problem comes into picture. But we cannot, because we'll have to look at in the train or in the aircraft what is moving on, that is Jagat. So therefore, or this world. So world is moving. So therefore, we'll have to move with that. You cannot remain aloof. Similarly, you are having the programs of Aditya, and Chandrayaan already is having. But I'll tell you, the Chandrayaan is a very good thing. What is being there, the limited power of the GSLV, which could manage to send the vehicles using a very simplified technology, and they are moving around the Earth to overcome the manual space, taking several loops. And Sukrayaan and Mars were orbits. The key thrust areas of landscape of aerospace technology, if you look at, we are to develop electronics and communications. And of course, the electronics, we are depending on the outside too much, and whereas we are not very self-reliant in that. And real-time sensing and sensor fusions, because today is the sensor things. And of course, the unmanned air systems and battery of small satellites. Satellite protections is a very important thing because of various regions. And this is a critical material and world-class manufacturing, because the Industry 4 is coming up. A lot of technologies are coming as the disruptive in nature. So naturally, you will have to keep pace with that time. And what is important from the both the civilian and also from the military application, stealth technology and deep space understanding is the need of the hour. And so also the, as I told, hypersonic and remaining life estimation and extension, because this is a very important aspect which we need to look at it, because the life is important, and so also the money, which plays a very important role. So if you look at the LCA, light combat aircraft, after that, we are having a plan of advanced medium combat aircraft, and which is basically is to be designed by the HAL. And this is a stealth multi-role fighter aircraft, and we don't have our engine, but maybe to start with, we can start with the GF 414 engines for propulsion. And as we are in the process of developing the engines, which I'm hearing for quite some time, now people are thinking of using 110 kilonewton class aero engine developed by the GTRE and other things. And this is the thrust area for this kind of technology. What is the requirement is the serpentine air intake, internal weapon bay and radar absorbing materials, and conformal antennas, because the antennas plays a very important role. And these are the technologies which are, has to be developed. And I'll tell you that there is we are having a lot of ambitious programs, but we always try to, do that such a way that things are very fast, because whereas the Western people do in a slow and steady, in a very gradual manner, and then they win the race. And I'll tell you, we are having now there is a, several millions of passengers have increased. Like it's a expansion, it's a phenomenal expansion. I call tsunami in the increasing in passenger aircraft. So therefore, but whereas all the, most of the planes we purchase from outside. And therefore, in UDAN, that scheme of government, that is the Civil Aviation Policy 2016, they have thinking of why not develop certain kind of aircraft our own, and already they have identified, because they want to connect the small cities and towns with the airspace so that people can travel for the business, for the education, for medical treatment and others. Keep in mind, there is another aspect I must tell you, that what happened to air pollution. So of course, that is the one concern. And then one is that what you will have to say that people are coming off with the 19-seater turboprop aircraft engines. And already, it is the work is being started by the NAL, and there is a SARAS, which is being basically timeline of production is 2020. I think it is little bit delayed according to my information. I may be wrong. And this is basically the Air Force is the basically buyer, and 19 seaters, and then RTA regional transport aircraft, which is 70 to 90 seaters. The projected demand is 250 to around 350. And by 2030, they are thinking that they can manage to produce that. And whenever it's talking about the, because you have to keep this time, you have to think in advance for the future, because today the entire technology is, basically for the pollution control, and then, a lot of amenities like fuel consumption is very important. Therefore, keeping in mind that they are going to basically decrease, having a technology which can manage to decrease the acquisition cost, operating cost, fuel consumption, maintenance cost, and also the emission, has to be lowered down by 70%. All others around 15 to 25% what they are claiming to have. And we'll have to see that how one can keep pace with the new norms being set by the Western people. And when you talk about these things, then a lot of things technology has to come, because you cannot go with the modern, rather you have to go for the advanced technology. The one advanced technology, what people are talking about is the blended wing body, which was basically developed by the NASA and talked about it. And that is for that, you need to have a have a very good, sleep or minimization of drag. And of course, you'll have to pay dividend in terms of fuel economy and payload. For that, you need to have a natural laminar airfoil design development. And of course, today people use composites and composite airframes, which is a very important aspect for making the aircraft lighter. And the next generation power plant, like today, if you look at, we are thinking of something 5th generation and 6th generation. That should be, the technology are changing rapidly in the Western, so also you have to keep pace with time. And there are several things I will be skipping because as the organizer told me, we're already late. So I'll be skipping some of them. Like, see, what important thing is that the more electrical and aircraft system has to be, and we'll have to go from more electrical to full electricals. And there are several technology one has to develop, is that basically GPS and WAS, ESVS, the enhanced synthetic vision systems, and automatic dependent surveillance systems, and the like anti-icing, anti-cleaning, and then abrasive resistant coating. These coatings are very important, and generally we get from outside country, and we'll have to develop ourselves, because these are when it is related to military, then it's difficult to get if there is a problem. So active, and there is also the integrated vehicle health. See, what I was talking about, the health monitoring, of course, maybe last 10 years I'm hearing, but in academic institute that is not working on. What I always feel that if you want to develop a technology, there should be concerted effort, and that has to be transferred to that, so that people will start doing research, and then you can go to, and also they will produce manpower to do that. And always we are on the firefighting stage, like kind of thing, then we are really in the trouble all the time. And then faster troubleshooting. So these are the technology one can think of. And as I was telling, the new way of looking at is that basically electrical driven aircraft. And this, of course, the E-Fan X already being started by this British Aerospace. Unfortunately, as learned from the internet that it was manufactured by the air, but they have canceled the things. And but that is the thing what I feel that one has to do, hybrid electrical testbed. And for that, a lot of technology has to be developed and a lot of research has to be worked out, and kind of things, hands-on experience are required. Like if you look at like high-powered DC generation system, electrical driven hydraulic systems, electrical air conditioning, pressurization, and also what I'm thinking is basically fuel cell power systems is very important, which can be. And there is also more technology. You can have a combustion system, micro combustors, which basically can convert directly to the electricity. That also one can. Several technologies are coming up. One can have to look at it. And when you look at this thing, what do we need to go to basically electric roadmaps. One has to have a policy for that, and also the academic people can start doing and experimenting on that. Building up no bleeding network to the no hydraulic network, and more electric engine to all electric engine. That is the things what we need to look at in future, particularly for aircraft. And the thrust areas, if you look at for important modeling and simulation, advanced safety. When I'm talking about this, generally what is happening in, at least in academic arena, students are very much interested to not to develop their own code, but they are more interested to develop some softwares. But rather today I'm trying to propagate that these are open softwares which are coming up in Western country. We can start and use that and also develop ourselves so that programming capability can increase. Because today, when I keep, go back to my own student time era, we are interested to develop programming. But today people are not interested to do that because that is not that easy because of shortage of time and other things. So high power electric motors and generators, cabin noise reduction, laminar active control, stealth technology is a very important, which must be developed indigenously because those technology people may not give. And advanced aerospace material and coating material always is important. So also they told structural health monitoring, integrated vehicle health management system is the need of the hour. Similarly, fly-by-wire control, avionics systems, and hardly will get very few people are there in avionics systems, particularly in academic arena, and we need to develop some kind of people so that who can give guidance. Data links and sensor and facility creations is a very facility, because a lot of test facilities we do not have. For example, high altitude facility. I remember that for cavalry engine, they went to Russia, and then Russia took a lot of money, and then then it. Of course, these are the projected demand for the civil transport aircraft. What people are thinking about. This is the LCA Mark 1, LCA Mark 2, 2A, and Navy AMCA. As I told, this is the basically advanced combat aircraft. And this is the new one which is coming up, is basically 5th generation fighter aircraft. What I feel that it is not that you'll have to think of 5th generation, you should go for the 6th generation, because when you think of that, then only you can go beyond that. So already Western people are talking about the 6th generation engines, and one has to look at that. And if you look at we are having the bottleneck. So far the aircraft is concerned, then we don't have our own engines, and cavalry engines is coming up. And this is a gas turbine, what you call UCAV. That is a 4th generation engine, and 5th generation, of course, this is the LCA and advanced that is coming up, MCA. And of course, the variable cycle engine, which is the new one, the 6th generation, which we need to work for that. And that is the plan. What I think the academic people always should be in the forefront of the technologies, so that they can really give some direction to that. And small expendable gas turbine engines for cruise missiles. And that is again the thinking of the Army, because most of the services from the Army and Naval and Air Forces kind of thing. So as I was telling, this is the technology program of different Indians' perspectives. So far engine is concerned, we are here in cavalry, and then people are thinking of F119, F135 engines. This is basically the 5th generation, and there is a 6th generation engine. As I told, the variable cycle engines, which is a very important one on us to look at, and is the intelligent control system. For that, for these 5th generation and 6th generation engines, you should have a ceramic matrix composites, fluid vectors system, fully authoritative digital engine control, integrated engine and flight control. These are the control technology is a very important aspect which we need to look at it, and indigenously one has to find out how to go about it. And I will not talk about it only, except I'll tell you that in the engine, so far there is concerned gas turbine engine, the main important component which really plays an important role where we don't have expertise, at least in academic point of view, that is academic institution, that is the turbo machinery. Very few people are there. And turbo machinery, it plays a very important role. And we need not only the talk about the compression system, which is very important, also the turbine. And in both the systems, you'll have to think of something very advanced design. And also the important aspect which we are lacking is the acoustic analysis to reduce noise, and active surge control by the tip injection, flow control by the aspiration. Several controls are there. That is also we need to develop. And similarly, the aerofoil design is the important one. And so also the thrust areas in the turbines will be, counter rotating turbines, ultra high lift turbine caskets, testing system has to be developed. And of course, I'll tell you that there are several things which need to be developed. So for and another next important aspect is the combustion technology, combustors. Combustors, we are finding a lot of problems so for cavalry engine, I was told. So therefore, we can also, those are also the technology which is a traditional one, but now we'll have to go for the advanced one. Like, for example, stage lean direct injection to reduce emission, partial ever rapid mixing combustion systems with advanced atomization kind of systems, like your internal mixing and then effervescent atomizers. Those kind of things has to be looked at it. And there are several fields I will not get into because the paucity of time. But what I would like to suggest that there are several combustion system technology which are coming up. Like, of course, the stage air combustion is now being used, and it's already Western people have developed a rich burn and quick mix and lean burn. And we are also involved in the developing the trapped vortex combustors and high temperature combustion. There's a catalytic combustion system which are coming up, and so also flameless combustion. There is a new concept which I have not worked, but it is in my mind that it can combine these combustors and the turbine together. That will be the idea which is lurking in my mind. But there is another important thing. What is coming up in Western country and what is the need of the hour is the fuel flexible combustors and hydrogen and blended fuel combustion system. What I think it's a need of the hour. So I'll not discuss about the turbine blade cooling because that is a very important aspect for the turbine and also other places. But two things I would like to say that one is the double wall cooling system which are coming up, and there is a mist cooling and the microjet cooling, which basically we are working on that. And beside this, there is several things which needs to be done. And for that, of course, both the experimental and numerical study has to be carried out pertaining to the gas turbine cooling systems. And if you look at the thrust areas, there are, as I told, that lower endless number is the key now for both the fighter aircraft and also the unmanned air vehicles and mini and micro UAVs. So therefore, but the data is not that much available, and maybe we'll have to design ourselves with it. So, and as I told that we'll have a various models kind of thing, high alpha angle modeling and, intake flow. So this intake is a very important aspect, particularly for the fighter aircraft and other thing, which is not many, expertise available. And for that, particularly for the supersonic and hypersonic, supersonic range. So when you talk about the CFDs today, we need not to only depend on the RANs, rather we'll have to go to the detached AD simulations and the large AD simulation, of course, the new norms. And so also we'll have to develop a kind of a fluid structure interaction and the flutter analysis. That is a very important aspect, as I told. Also the acoustic analysis is important so far the various places, not only in the turbo machinery but also the your exit kind of thing, particular fighter air. Similarly, the structural areas are also very important aspect, which as I told that it is both the transient thermal and structural analysis and is a need of the hours, and so also the damper effectiveness analysis, fuzzy probabilistic fracture mechanics, and damage tolerance design. So what I'm trying to mention those names so that the researcher can pick up at some of them and can look at it like, look, these are the things where the academic people can develop the tools and so that it can be really be useful for the developing better technology. So what I was telling about the facilities, what we need to have as a country is that like we altitude, high altitude test facilities is important. And so also the from the aerospace, of course, this is for the aircraft, but for the aerospace point of view, the microgravity test system is also important. Flying test bed in fighter aircraft, open test bed, and bird, ice, water, whatever is there, has to be looked at it. And there is a fan and compressor aeromechanical test facilities is an important one in a little larger scale in the national level. We need to have high temperature turbine test, which we do not have, and combustor turbine test. But as I was telling that Kaveri was using basically particularly high altitude test in the Russia, and structural test facility over speed and burst. This aspect is very important. And of course, the cartridge advanced material, a lot of things are coming up maybe. And what is the important variable cycle engine? As I was telling, the 6th generation engines has to be kept in mind, because we may think of going for that, because the Western people will dictate the terms and what is to be given. Otherwise, they will not allow your aircraft to move or fly. So therefore, we need to keep in time. And what I'm thinking, this is the fan and compressor blind stages. And coming back to that, I'm having another idea generally the compressor is subsonic. But people can think of having a transonic at least, so that the engine can be compact, and that is not even in outside. Very few countries are working, but we may work it out. And combustion, liner, HPT vents kind of things one has to look at. Smart sensor intelligence, because like today is the day of the smart. So therefore, we'll have to develop the smart control system, sensor intelligence control systems. And of course, the need of the hour, what you call the thrust weight ratio is greater than 12, and temperature is 2000, turbine temperature is basically 2200 Kelvin, hot end parts 2000 hours. So what I was telling, that electrical engines is the future, as people are professing. So, and also because of pollution and several aspects. So therefore, we need to look at all engine accessories, electrically driven, air for cabin pressurization, and also generation for the fans, because the immediately bigger aircraft one can think of using basically a turbo fan run by a motor. So that you can really have a technology, only engine you'll have to remove, and then rest of the things can be done very easily. So there is another very important aspect. I think DRDO has started some work, because they had invited me to some years back. I think pulse detonation engine, which is a very old technology. Rather, it is again coming up. Earlier it was pulse engine, but now it is pulse detonation engines. So that can be used basically in air breathing or the rocket propulsion. It can be for UAV in air breathing, and hybrid turbofan systems, and marine, and as I told. Then this PD afterburner one can think of. As I was telling, there is a new technology which is coming up, is basically distributed propulsion and blended wing. Blended wing, I've already talked about it. That means instead of one engine, as I've shown here in this figure in the green color, that there will be several small engines will be there, which will be really doing this, providing the propulsive power to drive the engine. And so if you look at the unmanned air systems, is the really very important today for the air, even for other purpose like your agriculture and other things. Nowadays, it is really being used even in your marriage party, also that sprinkle the water. I have seen some places. So therefore, the unmanned bomber aircraft, medium altitude, long range endurance, UAV, HAL, like high altitude, long endurance, solar UAV, rotary UAV, subsonic, cruise missile, unmanned. There are several kind of things. And there is a new concept which is people are talking about, is the swarm concept of large individual drones to act together as an integrated cohesive manner. And already I think China is already developing those kind of things. So from defense purposes or some other purposes also. And there is another thing what we can also do, because we are having several aircraft which are obsolete. Now you can have a scrap yard kind of things where you can take those things and convert into the unmanned aircraft, like vehicles kind of thing, and adaptable UAV. So if you look at, as Anuradha is told that when I was even student, ISRO was thinking of that single stage to orbit, now two stage to orbit, we are listening. Now they have started with that two stage to orbit vehicle power system. And they will start with the turbojet, then they will go to the ramjet, and they will go to the scramjet engines. And then after that rocket, and you will go. So if you look at, so already India has produced the cryogenic engines, and then we are having programs of, as I told, that ISRO is having a scramjet program, which is quite successful, and they will be using that technology in future. So far the hypersonic technology is concerned, there are several things one can think of, right? One can control effective hypersonic speed, and then shock interaction, and skin friction evaluation, drag prediction. So there's a host of the things one has to do, and one can, of course, the best way of starting the research on this actually is that you can start with the computational fluid dynamics and some develop the code, and then one can do. We are lacking, in that field. And there is a hypersonic air breathing propulsion system where the scramjet engine comes into pictures, and the scramjet design already, is going on, and then fuel injection devices, atomic techniques, and ignition and flame storage is a big problem there, and one has to look at. And indigenous CFD code for reactive, that is a need of the hours, as I was suggesting, that one can use the open form or other softwares to develop your own, because the open is available. And there's a thing, so I think endothermic fuels has to be looked at it, because that is the need of these engines, particularly the super scramjet engines, active control engine for long duration operation. And this is a single expansion ramp nozzle engine, which is a very important aspect that has to be looked at. And as I told that, there is a lot of things one has to do. Basically, the hypersonic experimental facilities, which is a need only in, I think, academic institute. ISC Bangalore is having, but other academic institute can think of. Because when you develop this wind tunnels, particularly from experimental, not only the subsonic already we are having, but the trisonic and hypersonic and cryogenic wind tunnel and shock tunnels, which are also required in other academic institute to carry out at least small scale, work, so that it can be. And as I was telling, emphasizing on that, we need to develop our own code so that we can really experiment a lot of things, and one can do that. And the rarefied flows, which is very not being talked about very much, which is very essential when we are going for a extraterrestrial kind of explorations, and which is very important to have that. And when you talk about the deep space, vehicles, then naturally you'll go for the propulsion system, this chemical, rockets having limitations. And then, of course, the gel propellant rocket engine one can help you, but it won't much, particularly deep space. But the gel propellant system can, and there is a laser propulsion system one can think of developing, and electrothermal engines, ion drive engines, solar cells, plasma propulsion, thermal vision, and continuous fusion. See, these are the all things what actually people have to look at it, and we should have some manpower with it to be trained. Particularly young people should be trained to undertake the research in this field, which may be used in future. So as I told, the stealth technologies is a very important, and which is having basically the reduction of radar cross section, combinations of shaping, various ones, and then you need to have a radar absorbing material, infrared shields, and exhaust cooling and shapings, and some other enhanced heat dissipations, reduced visual signatures, active signature cancellation, inlet shielding, and wind shield coatings. See, these are the technology where you need in terms of design, in terms of materials, even noise suppression, shorter response times, sensors, which is important. See, all these where we are lacking, and we need to develop, and those things which is very important, because people won't give you this. And there is a last things what I would like to say, that cyber physical security is a very, very important one. And we need to develop indigenous command and control for an aerospace, even in ocean systems, security and integrity of data, because data is a very thing, data handling, data mining, and then data science is coming up well. And one has to also be careful about the cyber attack on our installations and other things. So therefore, the cyber physical security is a very important field, and one has to look at it. Coming back to the conclusion, I can say that India has already demonstrated capabilities to develop aeronautical aerospace technologies. More emphasis must be provided for UAV, civil aircraft, hypersonic technologies, and also the various propulsive systems which are in the future. And we should have worked together to develop indigenous gas turbine engines, which is the need of the hour. Of course, the electric engines also is important, which you need to look at. And civil aircraft development must provide a high priority, as we are having a very boom in the flight space, and collaborative efforts among the academic industry and R&D house must be garnered to develop a resilience technology. And national advanced test facility, as I told, high altitude facility, hypersonic, supersonic wind tunnel, microgravity facilities, and several others like transonic, supersonic cascade tunnels has to be developed. And aerospace material, which I didn't talk about, it has to be developed indigenously. And so also the manufacturing system, as the industry 4 is coming up and a lot of new technologies are in the way, so they'll have to do. And as I told that the artificial intelligence and high capacity processing and pervasive cloud computing, these are the things which we have to be integrated with the aerospace engineering, which is already being there, but it has to be augmented. As I told, like rapid deployment of cycle in line with the industry 4 is the need of the hour to be competitive in the entire global market. And we can have a better future with the young people who are listening to this. They should come forward and develop and dedicate their life for this exotic and enigmatic field of aerospace engineering, which is the need of the hour. So with this, thank you very much. Jai Hind, Jai Bharat. And I am really thankful to taking the, all this material from this aerospace perspective, 2040 to 25 critical defense technologies and national security and DRD perspective. And what next in aerospace? These are the things I have taken help of to prepare and present you in front of you. Thank you very much. Sabko namaskar. Dhanyavad.
Thank you very much, sir, for your very elaborated, very exhaustive lecture, technical lecture on engines and all. You gave very good idea about all these propulsions. And I think in the present scenario of going on in the Russian countries and all, we can very well understand the technology and we can have a feel of the gravity of the technology which can be utilized here. So I think you have already taken a lot of time and you must be feeling slightly tired, but as a expert, we are going to have another session of panel discussion. And because we are already running behind schedule, as our lunch is also there. So I would request again to you, sir, to invite all other dignitaries or experts for this panel discussion on future of aerospace engineering. So hopefully slightly cutting short the duration, we can have panel discussion, sir. So I would request you to kindly proceed with the panel discussion.
Professor Pradeep, is it audible?
Yeah, it is audible, sir.
Actually, you should tell me who are the people in the panel discussion, because I am not aware. Of course, Professor Venkat Krishnan will be there. Dr.
Okay.
So please, this thing name wise, which are being decided, I think, by the committee.
Yesterday, I just asked the same question. What I was told, ASDB chairman will be chairing and members will be there, and 2 people from Kanpur local center. That's what I was told. Okay. Then Astana told that who will be there from Kanpur local center, they will decide and tell. Okay. This point yesterday we raised in the meeting before, so just to get clarity. Okay.
Okay, my suggestion would be rather I would put other way around with your permission.
Oh, sure.
Raghunandan is there. He can be one of the members. And Anuradha, Madam Anuradha is I think around, I guess. So she can be one of the members. And yourself.
He wanted to leave. She has taken permission from me. He just left. Okay.
That will be, I think.
Anuradha may not be available, I hope, because she has got some other appointment. I leave like that. She asked me right now, and I told, okay, you can leave.
Okay. So I think yourself, myself, and Professor Raghunandan, and anybody, I couldn't see full list. That is the problem with me. Maybe Madhavan is there. He can be one of the things so that we can.
I think I'm not able to see his name in the list right now.
No, I could see his name is there in front of me.
Okay, fine. We can request if available. Mr. Madhavan, sir, are you available, sir? I don't think so. Yeah.
Okay, I think what about Manish Tripathi?
पार्टिसिपेट करेंगे तो एरोस्पेस वाले सब लोग रहेंगे ना
So,
Same question I had, same doubt I asked actually. We had to.
okay, let us do this way. I think let me maybe.
Professor Raghunathan can chair definitely.
Yeah, I think that will be the best.
No issues, you can be there. Yeah.
Yeah. Mishra, I think at least the panel should be known who are the people going to talk, and they should. Professor Mishra himself can be there.
Yeah.
Dr. Krishnan, you're going to be there, right?
Yes.
Yeah, sir.
Dr. Vikram.
And Anuradha, is she there?
Anuradha, I think she has left, sir. She has got some other appointment in the afternoon. She called me and told me she has left.
So who else is from Kanpur? Anybody joining?
sir, good afternoon, sir. Vivek Asthana, I'm here.
Vivek Asthana is going.
Okay, fine. I think 4 is good enough. Am I right?
I think that's fine. That's fine. I think Professor Mishra, you have covered actually a wide canvas. You have.
It's only 30 minutes, no, sir.
Yeah, Professor Mishra has already covered a wide range of topics. I think there is not left much for us to discuss.
Okay.
But I think we will still look at the topics. So thanks for asking me to be with you on this particular point of time. We will talk about each one of us should not take more than 5 minutes, so that if there is somebody else outside this panel want to contribute, they should be able to do that. Sure. Now, let me just begin. As I said, Professor Mishra has really covered almost all the topics that could come to our mind. So this is future of aerospace engineering. Yes, I will say, I think you should look at it as it is actually going to cover the human activities for a long time. It's going to be there for our time to come, as I said. There is nothing like, our planet is extremely small. The rest of the universe is all space. So it is going to be there, and we are going to look at several different technologies which will grow. Even as it now turns out, as we see, there's a spectrum is, you're having a small drones, micro aerial vehicles. There is swarms of them, and going all the way up to deep space missions. There is so much to be done. And, whether you look at aeronautical, within the aeronautical part of it, which is within the atmospheric flight, you have many things to cover. As I said, small drones, where I see that the control is going to be the dominant discipline. Then you're talking of unmanned aerial vehicles, which are of a larger span, and you're going all the way up to unmanned combat aerial vehicles and so on. Now, there's typically, if I say in future, the question I would like to ask, I think the other panel members can say, is looking at the fact that the drones have developed, the way they are actually there, they are ubiquitous in the world today, and wherever there are shows, they are there, even in the military part of it. So, and then you have an unmanned aerial vehicles and the unmanned combat aerial vehicles. So the question I'm going to pose to the panel is, are we heading towards a totally unmanned atmospheric flight type of system, where you may not really have too many pilots to be trained, fighter pilots to be trained? Whether are we going to someday, considering the fact that we have the unmanned cars, driverless cars and so on, can we really take the leverage of this, what is happening on the terrestrial research, and say future even transport aircraft, will they be unmanned? Are we going to look at it? And that's the type of scope that we are going to have. people can express their views. Now, let me look at on the other side. If you look at the missile side, now you are seeing what is happening in the Ukraine war, that you have now hypersonic missiles already operational. They're not necessarily air breathing. They're hypersonic, all right. They're not air breathing. But then the fact that if you look at say hypersonic air breathing system, it has several possible applications. Defense is first, where they can use it directly. They're looking at space for a single stage to a two-stage to orbit. Or you look at future transportation aircraft. So there is an increase. So the question we need to look at, it is this part, should we invest in this technology much more than what we are doing? In my personal opinion, India on this particular sector, India is on par with the rest of the world. We can really be leaders in this particular area. Whereas if you look at all of this, we are not leaders, we are followers, whether it's space or other types of missile technology, aircraft development. This is one area where we can become leaders. So should we invest more in this? There is, of course, a third question I would like to ask all the members to say that, there is a security needs for the country. We need to have, whether it's unmanned aerial vehicles, or if you want to talk of drones, and then of course satellites and the space launch vehicles and so on. So there is actually a security of the country is paramount. We cannot afford to depend on foreign, the components and the major components for too long. One of the classic examples is in the military aircraft development, the engine part of it, which Mishra also referred to, where I think our dependence on the foreign technology has been too critical, which has happened in the past, happened with HF-24, it happened with LCA, it might happen with UCAF, AMCA, and so on. So we are actually too dependent on foreign technologies. We are good at aerodynamics, you might be good at structures, but you have problems in propulsion area. So should we really look at it? I can say my view, but then I would like the panel to do that. My last point I would like to say in this at this junction is the transport aircraft, which again Mishra mentioned about the fact that we need a large number of small size transport aircraft. We're talking of the RTA of 70 to 90 passengers, turboprop engine. So we should look at the possibility of small airports which can take, and the design of aircraft corresponding to that, which can really reach the remote parts of the country. It's going to be a big market for that, which is clear. Everybody knows about it. Exactly like that, you may have on the launch side, you might really look at, if you look at the satellite constellation systems that today are the low Earth orbit, you might require a large number of small launch vehicles ready to be launched at any point of time as a replacement of a satellite, repair of satellite and so on. There is actually a lot of possibilities. I think, so I would say saying that one key factor we should look at is privatization. A large number of smaller institutions should come up in the country. We can hire people. The best minds will come to the aerospace engineering, provided we can paint a good picture of what are the opportunities for them. That I think is one of the very critical systems. I can go on, but I leave it to the others. Let's say we'll talk about Dr. Aston. Would you like to start, because you are not spoken so far. Or Dr. Venkatakrishnan, would you come in, because Mishra has spoken?
Yeah, I think that is the best choice.
Venkatakrishnan, yeah.
Okay, I was just listening to you, sir. First of all, thank you so much for giving such a small time, whatever short span of time, a good thinking, whatever has gone into our mind, exactly you have spelled out. And that's what the direction, what the country also. In fact, instead of future of aerospace engineering as such, just like that, I would like to mention more about future of aerospace engineering in India in the context of national interest and context. Of course, aeronautics and aerospace engineering are two wings, which I don't know whether it's a line of boundary or anything, or I don't know. I have no idea at all. As per my understanding goes, both are interchangeably used in India as far as both is concerned actually. But under aerospace, aeronautics also comes, I understand. And civil aircraft is a thing which has been going on in the country for quite a long time. The offset policy of 1996 or whatever has come now has got only very broad and small engine components. As an engine, we have not got the handle so far because the offset policy, whatever we are getting is only airframes and bulkheads and other things, doors and door frames and seat and the bottom of the aircraft as well as the engine walls and some engine components. But as far as the Kaveri engine progress, of course, you all know that what is status right now. We are not reached the shores as we are really would have liked to actually after so many years, definitely. And we need to have a handle on the engine if you really want to have a headway in the civil aircraft area. Tejas also is coming up in a small way in a smaller aircraft and all. But if you want to go to Airbus, which is costing around 800 crores as per some of the surveys what we are having right now, we are paying through our nose. Each of our industry, including Indigo, everything 180, 200 we are buying per year. You know the kind of money flowing out of the country. We can do so much with this money, and so much of research can be done with this money. And we are still continue to buy from outside for our civil aviation requirements. And military, of course, Jaguar, Kiran, and all. We are little and Sukhoi and whatever MiG and all collaboration with Russia has given some lead to us actually. But we are stuck up with that. We are not further gone ahead with further that. Military aircraft, helicopter, ALH, and our other thing also. We are still, ALH also has come up in a nice way right now. I have to compliment HL for that. And as you mentioned, drones are also another area where it is picking up like anything. And drone-based radaring, so many things. Now radars are not fixed now. You must be knowing that our own colleague Taban Mishra was gone from Mishra, has started a startup right now with the synthetic aperture radar, which is all-weather radar now fixed in a drone, and it can move and it can be movably used. The radar can so you are not in the eye of the radar. The eye itself is moving now. Okay, so technology is far now advancing, and all. We can have the radars once fixed. It can be one radar can be used for other areas also, and it can move also. And apart from that, aerospace, if you talk about aerospace engineering rockets, of course, from the expendable rockets, if we are going to reusable launch vehicles, you are all aware that whatever you said, the thrust is required at the bottom, and after that, more control is required at the top for injecting the satellites. So TSTO always have been our best choice so far, and SSTO is still remaining a single stage to orbit, is still remaining a dream for us, all of us. It's a long way off. We have been talking about, I remember 15 years, 20 years back in case in Hyderabad, we talked about same thing. I remember air breathing was the concept there. I remember air breathing was the concept in Hyderabad. I participated. So we have not traveled too much from that. So future, if you talk, we need to accelerate these things. We need to see that air breathing technology coming up in the past so that the ISSTO can be pushed up. And equally, both aeronautics as well as your aerospace, both require ground support systems. So ground support systems are common, radars, antennas, and all these things. And of course, direct satellite communication is another one which is really, putting us into problem because we don't require towers and all like this. We can hold satellite to directly from the phone to satellite to phone. But that has got its own security problems, can be easily used by terrorists also. So we are not able to differentiate the frequency and streamline it and make it usable to the country alone. So there we are stuck up with that. There also we need to formulate some kind of a policy what need to be done. It should not be misused by the miscreants and anti-nationals. That is one thing. So security also is creeping in whenever communication is coming into picture. Apart from that, remote sensing and navigation also, as you told very clearly, sir, that constellation and more LEO constellations and all are going to. Another question, what is always in the air now, we have been talking to Airport Authority of India also. One project came to CBPO when I was heading CBPO. We could not do much, of course. Radha Madam also was there in the picture. Satellite-based navigation for aircrafts. So that is another thing which is which really has to be, because after your ATC, one ATC to another ATC, there's a blank zone. So, and even Wi-Fi also traveling, when you are using a Wi-Fi and connectivity while traveling also depends much. So satellite-based navigation for aircraft also is another thing to be pushed up. These are all aerospace engineering domain only. It need not be related to aerospace alone, because the sector needs all these things. Then only can be totally seen as a holistic way. And satellite, we need to have a trade-off. I don't know what kind of satellite we need to pursue now. There was some time back, it was told nano, then mini, then macro, then small, then huge satellite. Now we have got Mark 3 for 3-ton, 4-ton class. Whether we need to go for 6-ton class semi-cry and all, we are going now. But future with miniaturized avionics and other things and all, with all kind of connectivity coming in the shell itself, with the embedded shells and all, people have been talking about some time back, engraved silicon and embedded cells and all. Even micro satellites also have been talked about. So more of micro satellites launching in a smaller launch vehicles, which more cost-effective things are going to be future, means what we are developing will be obsolete then. It will be a disruptive technology. So we need to have a trade of exactly what direction the country need to progress. We need to keep a close watch on exactly what is happening around. And as we develop the huge launch vehicles, whether that is going to be used more or a smaller satellite launch vehicle, we are not still clear. That we need to clear. Technology is one thing. Exactly what is happening and what is going to be the future demand and requirements are another thing we have to keep in mind when you talk about futuristic policies. And green propellants, nuclear and electrical propulsion is another area where we need to have satellite propulsion in a much more controlled way and more of an endurable propulsion for deep space missions. We need to have endurable space propulsion, because not sustainable propulsion. We have to endure for quite a long time. A smaller propulsion, the thrust is not required there. The propulsion is only, force is very much less, but it should be available for 3.5 years, 4 years for deep space missions, and should be reliable and working as and when we require. So these kind of propulsion is actually not chemical propulsion at all, something different, because the thrust is not required. It is required for deep space missions. So sustainable energy and power systems also, because that is another thing with solar power harnessing, and that we are not done so far. We have been carrying our lithium ion cells so far in these areas. So all these things need to be demand based, and the kind of and another area where space can be easily used, even though I am telling about underwater communication. Exact underwater communication is going to be very difficult because of the refraction which is coming through the waves traveling in the water, and density of water is different in different areas. So it's very difficult. So far we are not through. So we need to travel the majority of the communication through space and then enter the water through some sport. So underwater communication also, space can be easily used. So these are all parts of aerospace engineering only. We can't be seen in isolation. So space is such a vast area where we need to have, and tomorrow we are going to have human space missions. We are not going to be constrained to a single planet species. Now we are going to be multi-planet species. Space tourism and space travel and interplanetary travel are going to be a reality. And 3D printing, of course, another technology which is coming in a big way.
I think time-wise,
I'm just coming to put last sentence. I'm just telling that in a nutshell, 3D printing for habitat building in other planets is coming in a big way with remote control. So all these things are very futuristic technologies. We need to check out policies for each one separately and need to deliberate and have committees working on this also. Have sustainable and very substantial progress in each of these headings, whatever I mentioned. I have just mentioned headings only to ponder about. Thank you so much.
Thank you, Dr. Venkat Krishnan. Now, who will speak now, Dr. Asthana or Dr. Mishra?
Sir, thank you, sir. We are already running out of time. In fact, I have requested Professor Praveen Pandey to join us and express his views in 1-2 minutes. He has joined. Actually, he is working in this field of combustion, hydrogen conversion for propulsion. Pandey, sir.
Dr. Pandey?
Yeah. Can you? Am I audible?
Yeah. Can you? I think we are, as I said, we are really running out of time. Maybe 2 minutes or 3 minutes, if you can express your views.
All right. As far as the space is concerned, hydrogen energy has got immense potential. Especially, it is it is having a much more calorific value per unit weight, and it is a pollution-free fuel. and it can be generated through renewables using solar also. So hydrogen is a very, very potential fuel for the space applications. And I have many more things to share, but since the time is less, I have done a lot of research work in the area of hydrogen combustion. So maybe in some other session, like next, I'm going to be there in the propulsion also, so I can share my views more there in that session.
Yeah.
Thank you for giving me time.
I guess Dr. Panda would require a very focused.
Okay,
forum.
thank you, Vandaji. I want to express my views in 1 minute. Actually, today we are moving to this communication side. I mean, this all offline works are going to be switched over to online. This communication technology is being advanced very rapidly, and for this we need this mobile communication and internet communication. So we have this communication satellites which may not help us for this online communication of mobile and internet. For that, if we go for the low orbit satellites, which may be used for these communication, and commercialize those satellites, so it will be very beneficial and add many things in our online activities. So this only I wanted to contribute.
I
so
think,
we think in that direction, this low orbit communication satellites, which may be used to communicate for this internets and mobile communication for various industrial applications.
So-called Leo
thank you, sir.
The idea is same behind. Let's now listen to Professor Mishra. You want to add more than what you have already said?
I've already discussed. I will not take more time, but what I will suggest that if what Dr. Venkat Krishnan has mentioned, that it is better to go for a smaller system. Small is beautiful. So if we can do the technology for that, then a lot of problems and will be, can be solved, but that is not that easy as well at the same time. But there is another thing, I have already mentioned several of them, because we need to have an engine development. We need to have a high deep space, non-chemical rockets like electrical, ion propulsions, and then nuclear, and then other things for the deep space applications. The other things I would like to say that there should be a facilities for the high altitude testing, then your turbomachinery, and then other testing for microgravity. All testing facilities should be there, national testing facilities.
Yeah. Okay.
And those also will be small things will be there in the case of some IITs and other things where the academic people can do research. There should be a industrial unit and there's thing. So that is very essential. And other thing is that there should be a communication between the research like ISRO and DRDO, and also the other thing that people, particularly academic people, should work in the advanced or imaginative kind of fields where they can produce the manpower. The last point I would like to suggest with the panel, maybe can suggest that there should be a study on the effect of aerospace technology on the peoples, ethical, social, and cultural, and other things. That is a very critical aspect which is missing. I think this much I will tell. Thank you very much. Thank you.
For that, the last point, I think we should leave it to, what shall I say, the people who are specialized in, yeah.
No, because this is actually this is a panel discussion. Whatever points will be, that will be discussed.
But I think just a point. Yeah, but I since the time is short, I think I don't want to go on. But I would like Institution of Engineers, that let me express you, to look at the fact that, are there enough opportunities for trained aeronautical? We are not getting the best minds into aeronautical or aerospace engineering in the country today because they are not seeing the opportunities for them in the country. And even those people who are good, they migrate outside. So there is a need to look at it seriously, how we can clearly show a path to a job potential in this area. That alone decides
who will come to this field? In the software, computer sciences, people are very sure where they're going to head. So their people are heading to that. Unless we have that clear picture, we cannot get the best minds into aeronautical and aerospace engineering. And if we are not getting the best minds, our growth or our progress is going to be very slow. So I think that's one critical. When I mentioned about the fact that we need actually a large number of private industries, other industries to take over, it's important for ISRO or DRDO to transfer technologies and make them all operational so that there are opportunities, large number of smaller jobs are available. Whereas these institutions like ISRO or DRDO should be looking at the research part of it. They should develop the technologies. They should really transfer it to industries who can create more number of jobs. Otherwise, we're stuck with a system where it's only a few institutions, fewer jobs, but we are now ending up with a large number of educational institutions where students are not really the best and they're not very much interested in the field. So that's one area if we do, I think there's a future of aerospace in the country will be, I think, will be solid. So I don't think my suggestion, Dr. Venkatakrishnan, since you are the chairman of the aerospace division, I think panel discussion on a more focused, narrower area will help. We are talking very broadly today, so it is here and so maybe I think in future you might look at it. You might just look at the point that you mentioned about the constellation of satellites and communication, the requirement of launching launch vehicles, whether small launch vehicles or large launch vehicles, or what is the best. You can really look at it a little more focused in the future. So thank you very much for asking me to be with you on this session also, and for all the rest that you have done to me today. I suddenly have seemed to have grown younger today. Thank you very much. Thank you, Mishra. Thank you.
Thank you very much.
This long time.
Thank you, sir. Thank you very much, sir.
Thank you very much, Dr. Asthana. Right.
In fact, this next session, this technical session 1 was scheduled from 14 hours and we are already late. So should we start it after 20 minutes? Because these participants were asking for the lunch break.
I think we should, because this is
2:15 now. So we will start this technical session at 2:30 instead of 14 hours.
Okay. Now it is 2:15, so we have to hurry and have 15 minutes lunch and come back.
Pardon, sir?
Now it is 2:15, no?
2:15, so 15 minutes for the lunch break. And then after 15 minutes, we may start our technical session.
Okay, fine.
Okay, thank you. Namaskar.
No problem.
Namaskar.
Okay.
Thank you.
Thank you.
Okay, sir. Thank you very much, sir.
Thank you very much.
Please,
Thank you very much.
all of you, please join by 2:30 then, please.
Thanks to all of you.
Okay.
Namaskar.
Okay, please join at 2:30.
Yeah.
So, Manish.
Yes, sir.
Okay, I was seeing you. That's all. Okay, fine.
Sir, there was one request. Can I start so I have one session scheduled. So can I start my session in the beginning itself?
I think you can ask our Asthana, who is controlling the sessions and all. No, Asthana can talk and you can always arrange. No issues. Vivek Asthana is the person.
Yes, Manish.
Yeah.
So can I? So my session is this N4/AS. So it is scheduled, I think, in the 4th number.
It's scheduled by which time?
I think it is in the 4th, listed as 4th in the session, during the session. So can I start it during the session, technical session?
Okay, you want to transfer this presentation? You are from technical session 4 to technical session 1.
Basically, I want to start it. Right now, it is in the number 4.
Because this is session chair and reference of the session, they will be joining at the scheduled time of the session. So it will be a problem there.
So Asthana sir, he is asking for he can present as the first paper presenter during technical session 1.
Same session.
Yes. Munishji, am I right?
It is
Yes, sir,
possible
yes.
you present your paper in the technical session 1 instead of
Yes.
your scheduled technical session.
No, it is in the technical session 1 only, but I want to start it in the initial itself.
Okay, you want to start it just now?
In the list.
You want to be the first paper presenter.
First presenter, yes, sir.
Yes.
First paper is this. Your paper is the 34 NCAS1. This numerical exploration of transverse sonic jet and hypersonic.
No. He is Monish Tripathi. His paper number is 34 NCAS 5. Numerical investigation.
Okay. This is numerical. ठीक है, तो you may present your paper at the starting of the session, at the beginning of the session.
With kind permission from the chair, Mr. M.M. Kothari, technical session 1, session chair, you can have the first paper presenter. Shortly we will start, sir.
Okay, sir. Thank you very much.
May I request the session chair, Mr. M.M. Kothari. Kothari, sir, are you here with us?
Yeah. I am there with you right from the morning.
Sir, it is fine, sir. Then this Manish Tripathi is requesting to present his paper at the beginning of the session.
No problem. Yeah.
Thank you very much, sir.
Thank you. Be ready with a PowerPoint presentation, Mr. Manish Tripathi.
Manish, you can share your PowerPoint presentation and be ready.
Yeah, I'll have a look.
Okay.
Because it is already late by 30 minutes now. You're from which place, Manish?
I'm from IIT Bombay, sir, Department of Aerospace Engineering.
Great. So I'm placed at Nasik only.
Okay, sir.
Okay. So what are you doing now? You are completed.
So I'm basically a postdoctoral fellow, and I'm carrying out my research under the supervision of Professor Pant, Rajkumar Pant, sir.
Okay, great.
On LTA systems, sir.
Okay. And you have done your graduation in aerospace only or mechanical engineering?
No, sir. I have done a dual degree in aerospace and avionics, and so everything has throughout my career it is only related to aerospace engineering, sir.
Oh, great.
So can you see my screen, sir?
Yeah. It's visible. Yeah. You have shared the screen also. No problem. You're from which place basically?
Sir, I reside. My native place is in Gorakhpur. However, for the past 20 years, I have been residing in Noida only.
Noida. Okay.
Yes, sir.
Actually, my video is off, I think, Manish, can you see me or my video is off, I think? Camera.
I can't, sir. I can't see.
No, I think, no, I am not able to see myself also. Right, I'll join with the device. From mobile, I'll join. Yeah. So your topic is, you'll be speaking on aerodynamics.
Yes, sir.
Okay.
So we will start this session. Has also joined. So we may start a little bit early.
Hello. Am I audible?
Yeah.
Hello, everyone. Good afternoon.
Yeah, good afternoon.
Welcome to the technical session 1 of 34th NCAS. 34th NCAS includes 5 sessions in total. These are aerodynamics, propulsion, structure, flight mechanics, design and system engineering. And our first session is on aerodynamics. Today, we are pleased to welcome Mr. Manish Kothari, member ASDB IEI as a session chair. He is having 30 plus years experience of owning and running successful manufacturing business and providing consultancy services to professional organizations. He is associated with several reputed industry associations and committees, BOT and past president of Nashik Industries and Manufacture Association, NIMA, biggest and pioneer industrial association in Maharashtra. Past chairman IEI Nashik Local Center and director Nashik Engineering Cluster. He is director of Maharashtra Pipes and Allied Industries Nashik for 3 years and former director of Pushkar Enterprises. He is associated with IEI for last 25 years. He is committee member of Nashik Local Center from 6 years, and he was also at different positions at Nashik Local Center. And committee member of Maharashtra State Center. I would request Mr. Manish Kothari sir to please say few words about today's session. Welcome sir. Welcome to the session.
Thank you, madam. And welcome everybody, Mr. Astana sir, Manish, and all the participants. In short, I'll just introduce myself. I'm a mechanical engineer basically, and we are having an industry in Nashik for last 40 years, who is an ancillary to Hindustan Aeronautics Limited and Air Force. We are into manufacturing of aircraft handling, material handling equipments and aero parts. So we are supplying and manufacturing and designing and supplying to HAL and Air Force. And the other things are that social things, chairman of NEMA, chairman of IEI, at various bodies, I'm director, board of trustees. Basically, I'm a chartered engineer also, a consultant in safety, a safety auditor authorized by government of Maharashtra. So I undertake audits for more than almost 400 plus industries, all medium, small and large industries in and around Nashik, or you can tell in Maharashtra itself. And so welcome everybody, all the participants, and all the best for the session. Manish, you can start, I think, within 5 minutes when Venkat sir or others are joining. I think Venkat sir, no, he's not there.
Okay, sir.
Other participants have come. I think there are 4 participants, I think. Kengshu, are you there? I think Manish, you and me, only the 2 of us are there. So Manish, you are doing research.
Yes, sir. I'm a researcher at IIT Bombay, sir. So I'm carrying out my research on LTA systems, the lighter than air systems.
Lighter?
Lighter than air systems.
Okay.
Yeah.
Have you been to Nashik or HAL anytime?
No, not exactly, but I would really love to have a visit over there, sir.
Because now there is a very good scope in manufacturing in indigenous aircrafts.
Yes, sir. Yes, sir. Correct, sir.
So you're doing research in some materials or the overall?
No, sir. My research domain is aerodynamics only, and as part of the different projects over here, I'm carrying out aerodynamic analysis of different LTI embodiments. Like one of them I'm presenting here during this seminar, and there are other different basically embodiments which I'm currently working in parallel. So trying to come up with a holistic overview of how the aerodynamics related to different LTA systems work.
Who else is there? Jatha there. Are you a member of Institution of Engineers, Manish?
No, not yet, sir.
Should become member immediately.
Yes, sir. Sure, sir. Sure, sir.
Online is available.
Yeah, so my collaboration as such, I'm not a member, but I'm also during this particular work of mine, I'm also a technical committee chair of an upcoming international event on LPA systems. So during that pursuance itself, I have contacted many high delegates from IEI, and in fact, IEI is a associate member for that event also.
Okay. Yes. Means IEI Maharashtra State is in association or IEI headquarters?
Pardon, sir? I think the headquarters, sir. Headquarters, sir.
Okay. So you can also conduct such programs with State Center also. Our office is at Haji Ali.
Okay, sir. I'll look into it, sir.
Yeah. If anything you require, you just contact me. I'll help you out.
Yes, sir. Sure, sir. Sure. So should I start the session?
No, if other participants and other dignitaries have joined on. Kengshu, are you there? Also not there. I think it is 2:32. We should start.
Yes, sir. With your permission.
Nobody else is there, I think. Bhatti sir was there.
Yeah, Bhatti sir there. Bhatti sir is there.
Yeah, he's there. How long you are there in IIT Mumbai?
So this is my second year of research. So till the next February, I'm here currently.
Okay. We'll be completing by next February.
Yeah, that is my plan right now. But yeah, extension is also on the cards.
Sir, may we start, sir?
Kenchu,
Yes, sir.
your lunch is finished. Shall
Yes,
we
yes,
start?
yes, 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 sir, yes.
Okay, Manish.
Okay, sir, may we start?
Okay, so greetings from me to the chair and all the dignitaries.
Just have a
and
minute,
the-
Mr. Tripathi. Just hold on. Vivek,
Sure.
sir. Just I have a word with our chairman of the host center before you starting our past paper. Vivek,
Yes,
sir. Vivek, sir. Vivek, sir, are you here?
Hello.
Hello.
Hello. Sensor.
Vivek, sir, kindly read out the citation of our session chair, Mr.
Madam,
Manish.
Madam, get it out. That is
Okay,
over
sir.
now.
Okay, sir. Okay.
Sir,
Okay. Okay, sir. Okay. Okay, sir. Okay. Manish Tripathi ji, please carry on, sir.
Yeah, let's time to participants here.
Yes, sir.
Thank you, everybody. And so I am Dr. Manish Tripathi. I'm basically a postdoctoral fellow with my research expertise in aerodynamics, and I've been carrying out my research on LTA systems in the Department of Aerospace Engineering at IIT Bombay in its LTA Systems Lab, under the supervision of Professor Rajkumar Pant, who is also the professor in charge for the LTA Systems Lab. And at this juncture, I would like to firstly convey my regards to the IEI panelists and the reviewers whose meticulous review helped us a lot in drafting this paper and coming up with a paper of reasonable high standards. So this is a brief outline of my presentation. I'll be initiating, giving a brief about the aerodynamics of LTA systems, that is the light air systems, which will be basically encompassing a brief overview of the literature survey that was carried out during the study. Then I will be basically detailing about the CFD investigations that I carried out during this particular paper, which will basically give details related to the numerical methodology adopted, followed by a brief overview of the solver validation that was carried out. And then based on this validation, what aerodynamic comparison was carried out between the two subjects of comparison, that is Lotte bare hull in comparison to a Lotte hull with full configuration. Then a brief overview of the qualitative analysis using the flow field visualization plots, and this will be finally culminated with the concluding remarks of the particular study. So just to give you a brief glimpse of the historical development of airships and how it evolved from being an uncontrolled balloon to a hybrid, evolving to be a hybrid future for the future. So the overall history of its development can be, in a nutshell, divided into these particular 5 parts. That is from 18th century, wherein many scientific inventors, they tried to come up with ways of carrying out their flight through different means, like the Montgolfier brothers in the 1784. They made use of this balloon to carry out their inception flight. Then from there this particular technology gained a lot of traction, and many other scientists and innovators tried to come up with their own ideas as to how to succeed in flight. And so airships or LTA systems played a very critical role in the overall flight technology development. So for instance, in the 19th century, this particular airship that you see, it was basically a derivative of this Montgolfier balloon, as in the technology was now evolving from a spheroidal shape to a more streamlined geometry, more in line with the overall aerodynamics that is required. So based on the credibility that this particular technology had, as it was able to succeed good amount of payload flight, many many other countries and companies tried to venture onto this. So for instance, in the 20th century, the Zeppelin rigid airships who came into the picture, which is basically considered to be a golden age for airships. So many countries like UK, Germany and Britain, they tried to, and Italy, they made use of these rigid airships during their passenger as well as their defense applications. However, and basically during the World War I, these airships were used on a very heightened level because of their different advantages. However, post World War, as well as followed by a number of dreadful accidents like the 1937 Hindenburg accident, the usage of these airships was significantly subdued, and they were mainly used for advertisement and tourism applications only. However, with the advancement of material technology and other other hybrid technologies, these airships are now again gaining a lot of traction, and many other companies, apart from only the Goodyear blimp, many other companies are trying to venture onto this, and the application is now being prolonged to more number of countries. And since there is an urgent requirement for an unconventional mode of transport owing to the increased fuel expenses, as well as requirement of reduced carbon footprint, airships being mainly governed by lift produced with the buoyancy, they are a good. They are being counted as a paradigm for future sustainable mode of transport. In fact, many missions involving space exploration are also trying to explore whether this technology can be utilized for their applications also. So, what are the different key airship design aspects? There are several other aspects, but in a nutshell, there are three main aspects. That is the aerodynamics, the fabrication, and the control aspects. However, in my study basically revolved around analyzing the aerodynamics of the various LTA systems. So, as far as the aerodynamics is concerned, there are 4 different forces that are generated by the aerodynamics that are responsible for the overall performance. That is lift, drag, lateral force, and the pitch of momenta. So whenever an airship is exposed to an external flow, the lift and drag forces are generated, which are further proportioned as buoyancy and aerodynamic lift, with drag being further segregated as viscosity and pressure drag. So since the airship hull is the most, it occupies most of the, it is responsible for most of the aerodynamic forces. The overall performance of any airship can be improved if we are able to optimally design this particular subpart, and if we are able to increase its performance, the lift and drag also both increase. So it is basically a question of how well we are able to optimize the overall airship hull, so that we can get reduced drag. And most of the study related to the aerodynamics has been basically revolved around mitigating drag penalties related to the airships. Airships, intuitively you may see that it is a very simplistic geometry, but when you go about overall analyzing, it's a very complex flow carrier, and there are different aspects related to the overall flow complexity like that is feature transitions, the wake formation due to the overall bluff geometry, the flow interference between the hull and various appendages related to interference drag. Then because of its body of revolution geometry, it is already amenable to the 3-dimensional flow, leading to vortical flow structure. The boundaryless separation because of its adverse pressure gradient region at the rear end, and most of all because of its high Reynolds number application it is strictly prone to the transition flow, that is from laminar to turbulent, and this further leads to the increase in flow complexity. Because of all these factors, the overall flow dynamics related to airships is highly non-linear, which further is a hindrance in analyzing the overall aerodynamics. And there is an additional factor called the added mass phenomena, which comes into picture when the airship is in accelerated mode of commute. So overall, we can very clearly see that the airship is a complex aerodynamic phenomena and could play a very critical role in the overall design optimization. So why it is essential to carry out aerodynamic study? Comprehensive understanding of these particular effects can lead to improved performance. For instance, in this study carried out in 1960, through their visualization, they were able to implement a propeller at the rear end, which led to performance improvement. We can also fine tune the placement of different parameters, different other embodiments like the optimal placement of propellers to increase the flow acceleration at the rear end, and hence leading to reduced vortical structure and hence drag. And then we can also carry out, through aerodynamic analysis, carry out optimal placement of different appendages like the hull fins or the leading edge root extension. We can also carry out through aerodynamic study the optimal selection of hull geometry. So there have been different ways as to how the aerodynamic study has been carried out in the past. For instance, the experimental study. So this was mainly during the inception phase, there was a lack of aerodynamic models. So most of the study during this era was carried out using flight test or wind tunnel experimentation. This basically involved boundary layer analysis, pressure coefficient distribution, and aerodynamic force evaluation. So most of the papers were mainly published through these methodologies in the 1920s to 60s. However, in the recent years, more number of papers are coming into the light, which are using different profiles that like the Lotte, Zuan, and ellipsoid profiles. The biggest disadvantage with this study is that infrastructure setting up is very high related to this because of the time and budget constraints. And the results are also prone to inaccuracies due to the errors in instrumentation and limitations pertaining to them. So then there are the other method called the analytical method, which basically makes use of semi-empirical relations based on wind tunnel data. And these are basically based on a certain set of assumptions and assumptions related to the real flow. For instance, the potential flow theory, which basically makes use of assumption as to incompressibility and irrotational flow, which is applicable for small angle of attacks and neglects viscosity. Because of the number of assumptions related to such a method, these are prone to diversion from the real flow physics. So further down the line, there have been further attempts to increase the realizability of the methods. So for instance, in this particular paper of 2019, the overall panel method was integrated with the boundary layer equations to further try to capture the real flow physics. Then there is a method for how to calculate the added mass estimation. In the year 2020, there has been a dedicated airship panel method that has been designed, which is a good method for analytic analysis. So these results are, however, although easier to obtain, they do encompass a lot of assumptions, which may lead to diversion from the real physics. And also there is a lack of universal model covering all flow conditions. So then we come on to the third method that is being used, that is the most notable used method in the recent past, that is the CFD analysis. So with the advancement of computational resources, these are the most adopted way of study. And the study, as far as the literature is concerned, the overall study has been carried out for different embodiments like the conventional airships, to carry out, to basically understand how the different flow parameters related to the airship flow are varying for different flow conditions. And then there is the study related to hybrid airships, wherein different hybrid airship embodiments are analyzed using the CFD methods to basically venture on to how efficient they are on an aerodynamic point of view. For instance, this 2017 method, paper by Carey et al. This basically is a very good paper on how computational fluid dynamics for a hybrid vehicle can be carried out, and what are the different challenges that a particular researcher needs to face while carrying out such a study. Now I'll basically try to discern what study I carried out during my study. So this was basically the study carried out to compare the aerodynamic performance of a bare hull and compared to the hull with fin configuration for a Lotte airship. So simulation was carried out in low subsonic and high Reynolds number flow conditions to compare the overall aerodynamic performance. So as far as the Lotte airships are concerned, these are basically, this was basically designed by Professor Kroplin and his team at Stuttgart University in the year 1919. Basically, this is the first solar-powered airship and have been mainly used for aerial photography, traffic monitoring, and various other applications. And these are also being utilized as reference configuration for different experimental investigations. So this is a small, brief overview of the overall profile of Lotte airship. And as I stated, the flow condition is high Reynolds number and the angle of attack condition are -2 to 10 degrees. So the adopted CFD methodology was that the model was generated using CATIA, followed by computational domain setup. The meshing was also carried out in sim scale solver, which basically makes use of the snappy hex mesh for 3D mesh generation. And then the particular solver, which made use of the sim scale platform, made use of the finite volume method, RANS methodology, and optimized solver strategy to carry out the numerical simulations. The post-processing was carried out using different post-processing softwares like the MATLAB and PyReview, and then we ultimately, based on this, we carried out the aerodynamic analysis. So as far as the numerical methodology is concerned, the model that we made use of during the study was the scaled down model of the real Lotte airship model, that is 1:20. And because of this, the length of the airship was around 0.8 meter with a fineness ratio of 4. And as far as the hull with fin configuration was concerned, the fins basically made use of the NACA 0018 airfoil placed at a distance of 0.6389 meter from the nose of the airship hull. So the overall flow condition you can see in this table, but the most notable thing that we need to be concerned is that the Reynolds number was around 3.9 million, and with the angle of attack varying between -2 to 10 degrees. As far as the mesh is concerned, the mesh was basically a hybrid mesh consisting of different levels of mesh refinement based on the overall flow gradient involved. The mesh size was 9.5 million cells, with mesh refinement being higher close to the walls. And further, we had also made use of the inflation layers to capture the boundary layer variations more appropriately. As far as the solver setup is concerned, the solver basically used during this study was the SimScale solver, which is a cloud-based solver designed in the year 2011. And in my solver, we basically made use of simple algorithm followed by a SST K omega turbulence model. So boundary conditions, as far as the boundary conditions are concerned, these were the boundary conditions employed during the study. followed by the solver setup, wherein the SST K omega turbulence modeling was used, and the a simple algorithm for pressure and velocity decoupling was used for the overall numerical computations. Firstly, to affirm the accuracy of the aerodynamic analysis involved, we carried out solver validation of a bare hull geometry related to Lotte airships, and this Lotte airship results were compared against the experimental results carried out by Funk et al. In the year 2003, and when we the overall comparison was carried out was for the CN and the CD plots. So as you can see, the solver was able to predict the results within an acceptable accuracy level of around 6.75%, and hence, since the trends were also in line with the overall experimental results, the same numerical setup was used for the hull with fin configuration. So then we carried out a preliminary analysis between the hull and hull with fin configuration, and as you can see, because of the presence of the fins, the overall lift slope is significantly higher for the airships, hull with fin configuration, to the power of 200%. 700%, and thereby leading to a significant increase in the lift for the hull with fin configuration. And simultaneously, drag was also significantly higher for the hull with fin configuration. And as you can see, after 4 degrees, there is a steep divergence in the angle drag performance for the hull with fin configuration. This is attributed to the fact that the presence of fins at the rear end, there is a significant amount of trailing edge vortices being generated, and thereby that leads to the higher CD values for the hull with fin configuration. The combination of the lift and drag variation leads to a higher aerodynamic efficiency for the hull with fin configuration of the tune of 200%, and thus the usage of fin, although may lead to increase in the drag, the overall combination is more efficient from an aerodynamic efficiency point of view for the airship, Lotte airship. So then we carried out profile visualization of the two geometries, and as you can see, for the Lotte hull with fin configuration, there is a steep increase in the flow separation at the rear end, and that leads to the higher drag values for the Lotte with hull fins. As far as the conclusions are concerned, the aerodynamic analysis was carried out using a cloud-based sim-scale solver, which is basically a cloud-based computing platform which does not require the usage of setting up of an in-house workstation. And this was a very big source of big motivation during this study, because Lotte airships encompass a lot of complexity and thus are amenable and would require a high-end computation setup to carry out dedicated aerodynamic study. So as a cloud-based solver was also able to capture these variations, this particular study could be a good motivation for the prospective researchers to make use of this platform to carry out their analysis related to Lotte, to airship analysis. So hull fin combination displayed, as far as the aerodynamic analysis is concerned, the hull fin displayed a significant increase in lift due to the LCO effect, which is also called the lift carryover effect, which was captured by the aerodynamic analysis. Drag also was significantly higher because of the higher flow separation, and the combination of this was that the aerodynamic efficiency was higher for the Lotte fin configuration. This study could be further collated with other studies for optimal fin placement and orientation, and this study will be further in my research further expanded to analyze the other parameters related to the particular aerodynamic analysis. So these were the different softwares used during my particular study. And I would like to firstly thank the IEI Kanpur Local Center for giving me this opportunity to present my work. in the presence of such dignitaries. And I would like to thank my supervisor and other colleagues, that is Manikandan, Pranshul Pandey from Manipal University, and other staff members of IT for helping me during this study. That's all from us. Thank you.
Thank you, Manish, for your enlightening presentation, and best wishes for your future work. Now, next we have M. Dinesh Kumar from School of Mechanical Engineering, VIT University, Chennai campus. He'll be presenting on aerodynamic characteristics of leading edge protuberanced wings featuring variously modified peak incidence angle. Dinesh?
Madam, one doubt there. Is there no time limitation for a paper?
There is, like, it is for 15 minutes for presentation and then 5 minutes for questions.
Because it has gone almost 30 minutes, that's why.
Excuse me. Excuse me.
Yes, sir.
That the next presentation, the first presentation of the session was by Vivek Bhati and Devashish Chakraborty. Why it is not been taken up?
Sir, sir, he is not there in the participant list.
It is there. It is very much there. I'm talking. He is there. I just now talked to him. Vivek Bhati. The first presentation was there, but they told that it will be taken up second. Now it is also not been taken up. Why?
Okay, sir. Sorry, sir. I'll check with this.
Follow some order.
1 minute. I think somebody requested before lunch, to be first, I think, and then at least the other person should be second. First should be second at least. No?
Yeah,
Yeah,
right.
Yeah,
okay.
fine.
Sorry,
Go ahead.
sir.
I think you go ahead. No, otherwise in order. Okay. He was permitted, I believe, by the chair because he wanted something. I was.
So
just
that's okay, but without informing,
No,
you cannot change.
You are correct. You are correct. I support you.
Okay, okay. Sorry, sir. So first we'll take presentation by Vivek Kishanlal Bhati. He's
Limited
from
to 15 minutes. Otherwise, no, this will go to evening. Otherwise, no.
Right. There should be some time also, limitation also.
So I would like to request Vivek. He's from Department of Aerospace Engineering, IIT Bombay. He'll be presenting on numerical exploration of transverse sonic jet in hypersonic cross flow. Welcome, Vivek. Now you can go ahead.
Am I audible, everyone?
Yeah, continue, Vivek.
You are audible. You are audible.
Okay, thank you. Just give me a second. Okay.
Can you make it full screen?
Yes. Okay. So good afternoon, everyone present here. Respected Dr. A.S. Kiran Kumar, Dr. P.V. Venkatakrishnan, Shri S. Somnath, Professor B.N. Raghunandan, Shri R. Madhavan, Srimati T.K. Anuradha, Professor D.P. Mishra, Dr. Ramakant Yadav, Mr. M.M. Kothari, Dr. Vivek Asthana, all the dignitaries and students present here. I, Vivek Kishanlal Bhati, am delighted to present the findings of the research paper, Numerical Exploration of Transverse Sonic Jet Injection in Hypersonic Cross Flow, that I have written under the guidance of Professor Devashish Chakraborty. So this would be the flow of the presentation. So as can be seen in the figure, numerous jets are being employed on a missile geometry. These jets are used at different locations as one at a time or simultaneously to generate desired change in the missile trajectory. Individually, these jets provide roll, pitch, and yaw motion to the vehicle. Finding a good configuration of jets is very essential to get accurate and reliable trajectory control. So now to literature survey. ASO carried out extensive experimental studies on transverse sonic injection from a flat plate into supersonic free stream. Erdem and Contis studied mixing characteristics of different gases at Mach 5 cross flow using Schlieren photography and two-dimensional particle image velocimetry. Hojaji studied the effect of free stream boundary layer thickness and jet momentum flux ratio. Stahl used 3 different jets individually and simultaneously positioned at different circumferential location and varied angle of attack and pressure ratios to interpret the complex flow field. Srivastava studied effects of various parameters such as jet thrust, jet position, and jet angle on missile control. Ashwin and Chakraborty simulated the experimental conditions of Stahl using a commercial software and obtained good match with experiment for all the combinations of angle of attack, number of jets, and their locations. Chan simulated and studied the jet interaction flow field for different angle of attacks on slender missiles with fins. Sriram and Chakraborty conducted numerical simulations of jet interaction problem and validated their indigenous codes by comparing the same with respective experimental results. Now coming to the flow structure. The figure shows general flow structure generated by transverse sonic injection into free stream of Mach number greater than 1. The interaction of the incoming boundary layer with the transverse sonic injection exhibits a complex flow structure, which consists of bow shock, separation region ahead of the jet, barrel shock, counter-rotating vortex pair, which is labeled as large-scale structures, and recirculation zones immediately upstream and downstream of the jet inlet. Coming to the motivation and overview of this paper. When fins are used for generating movement to change the angle of attack, it increases the overall weight, which leads to more fuel consumption and reduces the overall range of the vehicle, which is not the case while using jets. Time requirement for changing the trajectory using jets is much less when compared using fins to do the same. We know that threat to our sovereignty reduces not just by having attacking capabilities, but also by having capabilities to defend ourselves from similar type of attacks. Thus, the control using jets can be employed in defense systems that can be used to defend ourselves against ballistic missiles. Also, it is evident from literature review that jet interaction is a very complex and requires systematic studies to find out effects of various design parameters in getting accurate measure of aerodynamic forces and moments generated using side jet injection. But before we use these tools for practical design purpose, we need to make sure that these are also validated against reliable experimental results. For this, we have taken results of 2 experimental studies and have tried to compare the simulation results from this study with them. First is transverse sonic injection in the supersonic crossflow, while second is in hypersonic crossflow. The results of this study then are compared with the experimental results. The variables such as injectant penetration, spreadings are analyzed, and predictive capabilities of different 2-equation turbulence model are assessed. Coming to the first part of this study, we have the base case for supersonic from Sriram and inherited the boundary conditions from ASO. In table 1, you can find the boundary conditions for specific domains, and below it in table 2, you can find the variation of properties of free stream used to get the desired 4 different cases or comparison. The inflow conditions for the jet inlet and static ambient conditions have been kept same, while varying the jet momentum flux ratio, which led to change in the free stream Mach number and free stream velocity. 2 turbulence models, namely K epsilon realizable and K omega SST, have been used for comparison with experimental results. In both the figures, the normalized pressure on the center line of the wall has been plotted with results of K omega SST in the left figure and K epsilon realizable in the right figure. We can see that K omega SST predicts higher upstream separation distance as well as higher pressure just upstream of the jet inlet. Also, it can be seen that the jet momentum flux ratio decreases, the peak pressure ahead of the jet inlet rises, irrespective of the turbulence model chosen here. In this slide, we can see that the Mach contour and axial velocity contour results of K omega SST in the left figure and the right figure respectively. It can be easily noticed that the jet momentum flux ratio is increasing. After that, the separation point moves upstream and the Mach disk moves downstream. The circulation zone upstream and downstream of the jet inlet port, the separation shock and the bow shock are also captured generously. In this slide, we can see in the left figure that there is a lot of difference in the streamline shape at the outlet plane when both turbulence models are compared. In the right figure, K omega SST predicts higher concentration of the streamlines at the center as compared to K epsilon realizable. For the second part of this study, for side jet injection in the hypersonic regime, we have taken the experimental results of Erdem and Contes. The schematic of the experiment of Erdem and Contes is shown in the figure. 4 different case parameters were studied, of which have been shown in table 3. In this study, the jet inlet port condition is kept constant for all the cases, while for changing the jet momentum flux ratio, the ambient conditions have been changed. The boundary states have been kept same as in previous simulation. 2 turbulence models, namely K epsilon realizable and K omega SST, have been used for the comparison with the experimental results. Now, coming to the computational grid, it has been tried to keep the grid of the domain as structured as possible. Except the region near the jet inlet, which is kept circular in the shape, whole domain is fully structured. As when the circular jet inlet region was made structured, the elements became highly skewed near the jet inlet curve. Coming to the effects of turbulence model on flow structure, you can see Mach contour and axial velocity contour plots for jet momentum flux ratio 2.75 in the left figure and the right figure respectively. From both figures, we can see that K omega SST predicts higher upstream separation distance as compared to K epsilon realizable. Also, the lines seen in all the figures are Mach iso lines with Mach number equal to 1. Coming to comparison with experimental results at plane of injection. The wall static pressure normalized with free stream static pressure along the center jet injection line on the wall have been compared with the experimental results. A reasonable match between the experimental and numerical results are obtained for both the cases. Both the turbulence model performs satisfactorily, although K omega SST turbulence model performs much better than K epsilon realizable. In this slide, the jet plume width and penetration of the jet is shown in the left figure and the right figure respectively. It can be seen that the width of the jet plume is predicted higher by K epsilon realizable as compared to K omega SST. Also, with increase in the jet momentum flux ratio, the jet width also seems to be increasing. From figure on the right, it is noticed that K omega SST predicts higher penetration than K epsilon realizable, which was also seen in supersonic case. The variation of pressure drag force as well as moment generated about the leading edge is plotted in the left figure and the right figure respectively. It is seen that with increase in jet momentum flux ratio, both the pressure drag as well as the moment about the leading edge seems to be reducing with increase in jet momentum flux ratio, which was also the case in supersonic. While there was noticeable difference in the force predicted by both the turbulence models, the difference was negligible when moment was predicted for both turbulence models. Similar trend of decreasing pressure drag as well as moment about leading edge is seen. In this slide, we can see that there is not much difference in the streamline shape as seen in the figure on the left when both turbulence models are compared. But with increase in jet momentum flux ratio, the area covered by the streamlines increases. In the figure on the right, K omega SST predicts higher concentration of streamlines at the center as compared to K epsilon realizable. And streamlines in K omega SST also travel to higher upstream distance as compared to K epsilon realizable before turning back. Coming to conclusions, numerical simulations have been presented for transverse jet injection into supersonic and hypersonic free stream flow. Simulation captures all the essential flow features that were mentioned by ASO. Good match has been obtained with experimental results for both the cases. Parametric studies have been carried out with different jet momentum flux ratios. Force and moments about the leading edge are estimated due to jet interaction. Predictive capabilities of different turbulent models are assessed. Mentor's SST K omega turbulence model performs much better as compared to K epsilon realizable. The numerical methodology can be applied for practical jet control missiles. Coming to the references, these were the references used for this study. Thank you. This was the completion of the presentation.
Thank you, Vivek. We appreciate your efforts and we welcome the audience for questions. Do we have any questions?
Madam, we can take the questions after the session get over.
Okay, okay, sir. So now for the next research scholars, we have M. Jathaveda from Aero Combustion Modeling Division, Aerodynamics Design and Synthesis Group, Aeronautics Entity, Vikram Sarabhai Space Center, ISRO, Thiruvananthapuram. He'll be presenting on subsonic aerodynamic characteristics of a reusable launch vehicle. Welcome to the session. Jathaveda, you can proceed.
Good afternoon to all. Am I audible? Hello?
Yes.
Yes, sir, you are audible.
Yes,
Please
sir.
continue.
Yes, sir. Good afternoon to all the dignitaries and all the members present. I'm Jathaveda. I'm from Aeronautics Institute of VSSC. I'll be presenting on the subsonic aerodynamics characteristics of a reusable launch vehicle. This is authored by me, Kunal Garg, Vidya, Dr. Patil, and Dr. Ashok. All of us are from the Aeronautics Entity of Vikram Sarabhai Space Center, ISRO. So these are my contents of presentation. I'll be going ahead with the introduction, study configuration, results, and conclusion. So coming to this, so re-entry of spacecrafts in upper stages and their recovery is a quite challenging task. So in this entire process, the aerodynamic characterization is quite important and is an essential input as for the design of trajectory and structures and to design the structural systems. Now for this aerodynamic characterization, they can be carried out through various methods. One is analytical, theoretical, empirical methods, CFD, wind tunnel testing, or through flight testing. And then when it comes to re-entry bodies, there are different types. One is the ballistic body, like modules, like crew modules or something, and then semi-ballistic type, or lifting bodies like space shuttle and wing bodies. So here we're looking at the wing bodies, like we had RLB technology demonstrator, space shuttle orbiter, and X-34, X-37, which are winged re-entry bodies. So in this paper, we'll be dealing with the subsonic aerodynamic characteristics of RLB TD, and they are estimated using computational fluid dynamics tech methods at subsonic Mach number of 0.3. So this is the configuration as seen. You can see in the top right corner, the configuration of the winged reusable body, which has been considered. The simulations have been carried out using commercial software ANSYS Fluent, using an SST K-omega turbulence model. The conditions are taken of NAL scale and NAL wind tunnel conditions, and the kind of simulations are being done for a range of angle of attack from -5 to 20. So an unstructured grid has been generated with a 32 million cell count with a large domain to make sure that there are no domain boundary effects onto the solution here. And the domain and the grid can be seen in the bottom right corners. Here I'd like to acknowledge my colleague Babu for the grid on this part. And the boundary conditions given are far field for the outer domain, and body is considered as viscous walls. So before we move on to the results, after the simulations are done, consistency check is done and convergence check is done to see that the results are valid. You can see the bottom right figure, which shows the convergence of aerodynamic coefficients for one of the cases. For 3 cases, we've seen that this is for the lift coefficient. So it's not just the residuals we're looking at convergence in terms of the aerodynamic coefficients itself. So we can see that a good convergence has been obtained for cases ranging from -5 to 20. For this results, we can see from the Mach palette, the streamlines which indicate the direction of the flow that are coming, that is as the alpha changes from -5 to 20. The flow changes from top of the nose to the bottom of the from the bottom of the nose part, and we can see a low speed recirculatory flow at the base of this body. And in the bottom left figure, we can see the change in the stagnation region. That is, the stagnation point keeps getting altered as the alpha increases. And this data is be used for, such data could be taken for an air data system. So going further, we can see in the bottom left corner, the CP on the base region, CP being the coefficient of pressure that has been computed. So we can see that the coefficient of pressure also alters with the change in angle of attack. And when this is averaged and then plotted, you can see the figure in the bottom right corner, the variation of CP base on averaged coefficient of pressure over base. This trend is similar to what has been reported for the space shuttle body. And then we can see from the top right figures, there are about the palettes of CP as it goes from alpha -5 to 20 degrees. What we can see is as the alpha increases, you can see probably the left figures first. On the windward side, we can see at -5 suction and the fuselage nearby, and then slowly it builds up. And then on the leeward side, we can see that the leading wing, we can see a build up in suction. So we're seeing a highest suction, and we're seeing a higher suction as the alpha builds up. So this combination of, if we see at alpha 20, the high CP on the windward side and suction on the leeward side, this difference is what is causing the lift in these configurations. Now coming to the streamlines, we can see that the flow is attached in the inboard side of the vertical tail and the outboard side of the vertical tail. And when we see the alpha 20, that is the bottom right corner, we can see the attachment lines and separation lines on the fuselage, and then we can see the stray vortex trace on the inboard of the wing and the separation of the wing leading edge in the streamlines. Now, if we see the figure beside it, that is the vortices at this is at 20 degrees alpha. We can see that right along the fuselage, we can see a smaller vortex. This is coming from the stray vortex, which are more or less intact, whereas the vortices from the wings are kind of getting flatter and spreads over larger area. It crosses through the as it passes over the wing surface. Now coming to the aerodynamic coefficients, here we're plotting both CN and lift, that is normal force and lift. So you can see there from this curve, there is no stall-like behavior, although there's a minor slope change at the higher alpha. And when we see the component-wise distribution for this particular normal force, we can see that the fuselage contribution is also large enough. That is, it's about 30 to 35%. So in this kind of configuration, the lift is generated not only from wing, but both from fuselage also. So now coming to the axial force and drag, we're seeing that the axial force is positive at small angles and becomes negative at larger angles. Whereas the drag exhibits a conventional behavior of increasing with the increasing alpha. So here again, if we see the contribution of various components of the geometry, here again we can see that the wing gives the negative value on axial force, which is the reason why the CA becomes negative. And this is occurring because if you recall the previous figure, maybe I'll just go back one slide to show that. Two slides. So you can see that there's a large suction on the leading edge. So this kind of creates this negative drag on this particular configuration. Now coming to the pitching moment coefficient, the pitching moment is computed about the CG of the body, and the curve indicates a pitch down moment, and it is increasing with the alpha. So to compensate for this, the aileron deflections are needed to counter this. And based on this, we can see that the natural trim occurs at negative alpha, and the slope being negative indicates longitudinal static stability for this configuration. And the pitching moment that has been computed compares well with the results at the reference, except for the higher angle, there's a slight variation with the results. So to conclude, we've done the subsonic aerodynamic characteristics of a RLVTD configuration using CFD at Mach 0.3. So ANSYS Fluent Solver with K omega turbulence model and unstructured grid are considered. The variation on the seat coefficient pressure over nose cap, fuselage base, and complete vehicle have been discussed. And flow patterns and vortex visualization at different alphas for understanding flow physics have been presented. The axial force, drag, and normal lift and the component-wise contribution have been seen, and the static stability has been seen through the pitching moment curve, which compares well with the reference values that are available. That's it from me, sir. Thank you very much.
Thank you, Jadaveda sir, for your insightful presentation. So the next presentation we have is the topic, a computational investigation of the aerodynamic characteristics of trailing edge serrated wing and aerodynamic perspective. This will be presented by S. Arun Vinthan, A. Ahmed Sarun, R. Vaitiswaran, K.B. Babu from the Center for Flow Control of Research and Education, Kristen Coil, Tamil Nadu, India. So without any further ado, I would request you to please join this session and start your presentation. Anyone from your presentation, are you there? The names I have called upon. We did receive a message that you are having issues joining this session, but we have sent you the link again. So do check and please join the session. Is he there? Hello, is anyone from the third batch here? Okay, I think they are having some technical issues related to this. So we will move on to the next, team. So can you show me that? Okay, so we will now start the presentation for this one, right? Yeah. For aerodynamic characteristics of leading edge protuberant wing featuring variously modified peak incidence angle, and to be presented by M. Dinesh Kumar, R. Shakti Krishna, S. Deveshwaran, G. Vinayagamurthiya from the School of Mechanical Engineering, VIT University Chennai campus, Kilambakkam, and S. Arun Vinthan from the Center for Flow Control, Kalasalingam Academy of Research and Education, Kristen Coil. So if you are present, I would kindly request you to start your presentation. Is anyone there from your team?
Yes, sir. Good afternoon, sir. I am Shakti Krishna here.
Yeah. Welcome to the session, and please continue.
Good afternoon, one and all present here.
Can you please maximize it?
Okay, sir. Good afternoon, one and all present here. I am Shakti Krishna, and I am going to present a topic on aerodynamic characteristics of leading edge protuberance wing featuring variously modified peak incidence angle. Sir George Cayley designed and built airfoil, and which we have been using for more than 200 years. And this model is used in engineering such as like wind turbine blades, propellers, and marine radars. And the flow over the airfoil needs to be attached to increase in operational capability and efficiency. Therefore, the flow of the airfoil has a direct engineering significance. In aerodynamic, there are three flow control categories. One is active flow control, in which we utilize energy, for example, like actuators, and in passive control flow. In passive control flow method, energy doesn't require. Like we modify the geometry, we introduce what is in hybrid flow control. The combination of both active and passive method is utilized. Many engineers draw inspiration from nature, and these are the examples. Vikram, it has been inspired from bird rock, and the stealth, it has been inspired from the hawk, and many devices like the serrations has been inspired. And the LEP model, the leading edge protuberance in the wing, has been inspired from the unpacked wave. This structure is called tuber shell, and it gives the whale high acrobatic maneuvers and helps in swimming. In the LEP, these are the devices which LEP have been applied. LEP helps the airfoil in achieving gradual start in coastal region, thus maintaining the stability. And the flow attachment area is highly compared to model without LEP, thereby increasing the aerodynamic characteristics. The research cap of our research is there have been many studies on effect of LEP with variation in amplitude and wavelength. So we have changed the inclination angle of the peak with respect to the trough. This is our research. The model parameters have been listed in the table. We have been choosing the NACA series 6 series 34021, which have similar, which resembles the shape of the unpackable keepers, and we've been using a Reynolds number of 20×10⁶, and the peak incidence angle is 0 to 600 by difference of 2. एम्पलीट्यूड
डॉक्टर सुमित खिमनसरा बोल रहा हूँ।
हाँ बोलिए।
बात कर सकता हूँ, अभी फ्री होंगे?
हाँ हाँ बोलिए।
हाँ, तो वसुधा ने आपका नंबर दिया था और अभी मेरा बैकग्राउंड ऐसा है कि मैं माय एज अराउंड 44 एंड माय सन इज अराउंड 14 इयर्स नाउ। तो वसुधा के पास काउंसलिंग के लिए वो जा रहा है और उसके पहले से वो डॉक्टर येवले से कुछ ट्रीटमेंट ले रहा था।
डॉक्टर येवले मतलब न्यूरो फिजिशियन।
करेक्ट। कैन यू प्लीज? और उनका कहना था कि वो टिक्स का कुछ उसको प्रॉब्लम है। आई मे बी रॉन्ग इन द टर्मिनोलॉजी। तो उनका एक ट्रीटमेंट भी चालू है उसका दवाइयों का।
Excuse me, who is this? Can you please stop for a while because a session is going on right now?
Yeah. I think everybody can mute unnecessarily, no, because everybody can mute. It is causing disturbance.
Sorry, Dinesh, for this disturbance. You please go ahead. We are giving you 2 minutes for this. And please, anyone else, no disturb like this because the session is going on right now. So please keep yourself muted.
The wavelength of the LEP is 12% of the chord, and the wavelength is 50% of the chord. The normal mean normalized chord length is 1 meter. In this experiment, we have used K omega SST model, and we did a grid intermittency test to identify the suitable grid size. From our test, it is clear to note that after 5 lakh nodes, 5 lakh mesh value, changes in coefficient of lift and drag values nearly, the changes in them is nearly negligible. So we took value as 5 lakh nodes. These are the images generated using the Gambit software. Here we have, this is the LEP model, and we have tilted the peak with 2 degree, and here 4 degree, and here 6 degree. The flow attachment area decreases with increase in angle of attack. So due to the lower angle of peak compared to the trough in LEP, flow attachment behind the peak region is more compared to the flow attachment in the trough region. And at the same time, this is the cause of the degraded performance in the pre-stall angle, like before 10 degree, 0 to 15 degrees. And in the pre-stall region, the peak experience same low angle of attack compared to the high global of attack in lift produced in the pre-stall region. This explains the reason for decreasing coefficient of lift with increasing downward peak incidence angle for below 30, and this trend changes after angle 30 degree, that is post-stall angle, because peak experience lesser angle of attack than other regions. So there is some flow attachment presence. The effect of peak downward incidence on drag coefficient of for the T6, for the angle 6 peak incidence angle, exhibits significant reduction in at both pre-stall and post-stall angles. High angles of attack alpha increases, peak incident angle decreases drag coefficient. This is due to the variation in cross section of the protuberance is more when compared to baseline LP model, which may increase the mixing of flow and cause the flow to be more turbulent, and which results in even more reduction in drag than baseline LP. The aerodynamic efficiency of LEP-B with greater angle of incidence performs better than the LEP with lower angle of incidence. The peak aerodynamic efficiency of the LEP-B can be observed at 10 degrees. And for all incidence angle after 10 degrees, the reduction is gradual and only in theta 6, like that is T6. And the aerodynamic efficiency increases with increasing downward peak incidence angle. The addition of peak incidence angle reduces the drag and improves the lift. For example, for instance, at 25 degree, there were 12 and 50% and 22% drag reduction, or angle 2 and 4 and 6 were observed. And in the lift case, at angle 45, there were 3 and 3.9% and 5.69% lift increase was observed for angle 2 and angle 4 and 6. Thank you.
Okay, thank you, Dinesh, for your great efforts. We have another session, another team left, but they're having some issues joining this panel. So right now, I would like to, like, if anyone has questions regarding the sessions we have had, you guys can continue with your questions, because one team is unable to join the panel right now due to some technical issues.
Suman, I think nobody has any questions. The dignitaries, do you have any questions? Venkat sir, Bhati sir? Suman, did you call that participant again?
Actually, sir, we are speaking to him through this Zoom call only. We don't have his number. So he's saying that he's unable to join the panel thing, panelist. He's joining as an attendee, but he cannot join as a panelist. So he's unable to share his screen and speak also.
Because as it is, we have got 10 minutes now.
Okay, so we have, I think we have another participant,
Yes,
M. Harish. M. Harish, can you please speak? Like
Harish is there. Harish is there.
Yes, sir. Can everyone hear me, sir?
Yeah, yeah.
Excuse me.
Yeah,
Okay,
Am I
so let
audible?
me introduce you once. Harish, are you ready with the presentation?
Yes, sir. Yes, sir. Sir.
M. Harish, K.P. Dhanapala Krishnan, M. N. Maheshwaran from the Department of Aeronautical Engineering, Hindustan Institute of Technology, Coimbatore, will be presenting on CFD simulation over a 2D axisymmetric re-entry capsule configuration. So please go ahead, English.
Hi, sir. Sir? Hello, sir. Sir? Sir? Am I audible to everyone, sir?
Yeah, yeah.
A very good afternoon to all the panel members. So I am Harish. I am working as an assistant professor from Hindustan Institute of Technology, Coimbatore. So my paper title is CFD simulation over a 2D axisymmetric re-entry vehicle capsule configuration. And this is about the outline of the presentation. So we have the abstract, we have the configuration studied, we have the computational tools involved, the boundary condition in grid dependent study, results and discussion, as well as the conclusion. So we have the abstract here. So apart from the blunt shape of the re-entry vehicle, so this thermal protection system plays a major role when we usually re-enter into the Earth atmosphere. So as this thermal protection system failure in the capsule, so ultimately it can cause damage to the vehicle. So it is important to concentrate on the loads, the various pressure loads, as well as the thermal loads that acts on the vehicle when it, especially in the re-entry vehicle, when it enters into the atmosphere, it plays a major role, that too at a very high altitude of greater to about 100 kilometer. So thus it is important to measure these pressure as well as the other loads that acts over the vehicle. So we are carrying CFD analysis for a re-entry vehicle configuration, in specific about the Mach range of 3 to 5. And the configuration we have chosen for the study is similar to the Apollo, that is Apollo AS 202. So where you can see the length of the re-entry capsule, the as well as the radius of the blunt nose, the height of the blunt nose. So this is the configuration I have taken into it for the CFD analysis. And the tools involved for this CFD simulation. So for meshing, GridGen have been used to generate this multi-block structured grid, and ANSYS Fluent has been used as a solver in order to do the simulation. And the grid distribution, in order to capture the boundary layer thickness, fine grids have been made closer to the boundary. You can see this is the four-body geometry of the re-entry vehicle. I've taken only one half of the vehicle due to as it is axisymmetric. So in order to capture the boundary layer thickness, fine grids have been made near to the body surface, as well as the core grids have been made outer in the outer domain. And the boundary conditions that has been applied for this CFD simulation is, so you can see this wall is actually the re-entry vehicle, and we have defined the symmetry boundary condition along the axis, and we have the pressure field boundary conditions in the outer domain. So this is the boundary conditions that has been considered for the CFD simulation. And the input conditions for this CFD simulation, where we are doing the CFD simulation for the Mach numbers 3, 5, and 7, and the pressure and temperature. So we have taken the region ahead of 100 kilometers. So we have taken the constant pressure and temperature that altitude, and only we are varying the Mach number for the simulation, that is from for 3, 5, and 7. And the grid independent study has been done with 3 different grids, where for all the 3, the total number of grid cells differ from each other. So we have taken 20,000 grid points, 45,000, as well as 60,000 grid points. So 3 different grids have been generated with different in the total grid points, 20K, 45K, as well as 60K. And this is the grid that has been generated over the re-entry capsule. As I said, for grid independent study, we have taken 3 different grids. So this is grid 1 to about 20,000 total number of 20,000 grid points. And this is grid 2 over the vehicle with 45,000 grid points. And this is grid 3 over the vehicle with 60,000 grid points. So the CFD simulation has been done with all these 3 different grids, and by plotting this pressure distribution over the vehicle, we have found that you can see that 3 different curves, CP curves, have been plotted. This blue color curve is for grid 1, where with the total number of 20,000 grid points, and this red color curve and this green color curve, they are of 45,000 as well as 60,000 curves. You can see that with the increase in grid points, that is for 45K and 60K, this red color and green color curve, you can see that with further increase in grid points, the CP plot remains one and the same. So the optimum grid has been considered as grid 2 from the grid independent study, as this grid 2 and grid 3 with the grid points 45,000 and 60,000, since the SCP plot remains one and the same. So with the further increase in grid points, the SCP plot will always remains the same. So the optimum grid has been taken as grid 2 from the grid independent study. And this 45,000 grid points has been taken, that is the grid with 45,000 grid points has been taken for the further CFD simulation with by doing the simulation with 3 different Mach numbers, say 3, 5, and 7, and the various aerodynamic characteristics like the coefficient of pressure, the location of shock wave, as well as the variation of Mach number and pressure over the vehicle has been extracted from the CFD simulation. And the turbulence model we have used for the simulation is the K epsilon turbulence model with the same input conditions, as I said, for without changing the pressure and temperature. Only the Mach number has been changed for the CFD simulation. And this is the coefficient of pressure distribution for the Mach numbers 3, 5, and 7, where you can able to see that the variation of pressure over the vehicle, so as it is maximum at the stagnation point, that is it is near to 2, where this maximum, or you can say the peak in CP is due to the stagnation point that occurs on the front end of the re-entry capsule. So this is the reason, and later over the vehicle there is a drop in pressure, and there is a sudden drop in pressure over the vehicle due to the occurrence of the shock waves over the vehicle. So we'll be having a bow shock as well as these expansion fans. So that can be much clear from this Mach number contour. You can see this is the re-entry capsule vehicle, and this is the vehicle bow shock that occurs ahead of the vehicle. So due to this vehicle bow shock, you can see this there creates a subsonic region near to the axis, as we have defined. The boundary condition is symmetry. You can see near the symmetry line behind this bow shock, you can see a subsonic region which is similar to the flow behind the normal shock we have. And similarly over the vehicle, you can see these expansion fans that has been created over the vehicle, which actually causes a increase in Mach number downstream behind these expansion fans. So as these, when we have these expansion fans, the flow will be accelerated, and when we have these occurrence of occurrence of oblique shocks and normal shock, the flow will be decelerated. So due to the occurrence of these expansion fans over the vehicle, the flow gets accelerated, and you can see this red patches as the Mach number increases behind these occurrence of expansion fans over the vehicle, or the re-entry vehicle, that is over the upper half of the re-entry vehicle. So the same phenomenon has also been observed for the Mach numbers of 5 and 7, So this is the figure for Mach number 3. So you can also observe the similar flow pattern for this Mach number and 7 also, but with increase in the free stream Mach number. So that is the reason you can able to see the changes in color. You can see that this red color is almost about to 3, and these for Mach numbers 5 and 7 we can also observe the similar flow pattern, but with the changes in color as these free stream Mach number has been increased due to for Mach number 5 and 7.
Hello,
And this is
Harish.
the pressure contour over the re-entry vehicle for Mach number
Hello,
3.
Harish.
Yes, ma'am.
I would like to request you to go through your presentation more quickly.
Oh, okay,
Time
fine.
is there. Yeah.
Fine, fine. Thank you. So you can also able to see a drop in pressure behind the expansion fans, as we have also seen from the Mach contour plot. Behind the Mach contour, the flow gets accelerated. That is behind the expansion fans, the flow gets accelerated. So the same phenomenon can also be seen in the pressure contour plot. Also, you can see a drop in pressure behind these expansion fans. And so for Mach number 5 and 7 also, you can see a lot changes and drastic changes in pressure downstream behind the expansion fans, as the case for Mach number 5 and 7. And also the vector plot in order to capture the flow separation or circulating region or wake region. So a vector plot has also been taken, where you can also able to see a reverse flow pattern. Reverse flow has been observed in the rear end of the vehicle near to the symmetry line, and later after some distance, as the flow moves downstream away from the vehicle, this flow separation region, it has been reattached by a distance later later along the symmetry line downwards away from the vehicle. So the same flow separation region has also been observed for the other Mach numbers 5 and 7 also. Later, as the flow moves downstream away from the vehicle, this separation region has been reattached by a distance later along the symmetry line. So this is also observed for Mach number 5 and 7. So the conclusion after the CFD simulation over the 2D axisymmetric vehicle is the peak in pressure has been observed for all the Mach numbers of 3, 5, and 7. As you can able to see this negative value of CP as the flow moves downstream over the vehicle due to this occurrence of expansion fans as the flow moves downstream, or I can say the rear end of the vehicle. So due to this, there is a drop in pressure over the vehicle near to the downstream, which we can also observe the flow separation region from the vector plot. So that is the reason this CP falls down to a near to a negative value in the downstream of the vehicle. And also from the Mach contour plot and the pressure plot, the vehicle bow shock has been observed ahead of the vehicle for all the Mach numbers 3, 5, and 7. And over the vehicle, the expansion fans have been observed, which actually causes the flow to be accelerated due to the occurrence of expansion fans. And at the downstream of the vehicle, in the rear end of the vehicle, this flow separation region has been created, and later the flow has been reattached by the distance away from the vehicle along the symmetry line. So this same phenomenon has been observed for all the 3 Mach numbers, but as the free stream Mach number increases, the acceleration of the flow has been increased to a greater number for all the 3 Mach numbers 3, 5, and 7. And these are the reference paper taken into the consideration for the current study. Thank you all. I have done my presentation.
Yeah, thank you, Harish.
Thank you.
Any questions?
Mr. Harish, one question, actually a clarification on the inputs. Am I audible?
Yes, sir. Yes, sir. I can.
You studied it for 100 kilometers.
Yes, sir.
What was the purpose of doing that? Because their air density is very less.
Sir, actually, the rocket vehicle, what I have taken into consideration is the re-entry capsule. So why I have taken that about 100-kilometer altitude is as the rocket vehicle, for example, say our PSLV as well as the GSLV, the upper half we call it as a heat shield as the payload fairing. So it will be two halves. Once the vehicle crosses the 100-kilometer, the two halves of the payload bearing will be separated and the satellite will be put into the orbit where the air temperature as well as the pressure and density at that altitude is very much important as a similar case for the re-entry vehicle when it enter into the Earth atmosphere region. So that is the reason I have taken those input conditions, sir.
Because situation becomes severe as we come down in the case of a re-entry vehicle, unlike a launch vehicle. So something like 65 kilometers or something like that, some 65 to 30 kilometers, this effect will be aerodynamic effect, heating effects, all will be much more. Beyond that, it starts slowing down much. So that's why I asked this question.
Okay, sir. I have taken a relation similar to the rocket vehicle, sir, as they separate the two halves and as the satellite is put into the orbit. So I have taken into that consideration by comparing the effects what actually happens the case of a re-entry vehicle. That is the reason, sir.
So this is not a sponsored study. I mean, somebody has given you. It's a more academic exercise.
Yes.
Okay.
Yes, sir. Yes, sir.
Okay. Thank you.
Thank you, sir.
Hello. Am I audible? Thank you, Harish, for your insightful presentation. Now,
thank you.
We move forward for question answer round. So, do we have our first presentee here, Manish?
Excuse me, ma'am. Ma'am.
Yes.
Ma'am. This is Vaitishwaran, ma'am. I message you at the message box. I can't able to open the mail again, ma'am. Can we resume with this ID?
Yeah, sure.
Okay, ma'am. When can we present, ma'am?
Welcome, Vaitishwaran.
Okay, ma'am. Thank you, madam. Can we present now?
Yeah, you can present.
Okay, thank you, madam. Good afternoon to everyone. Sorry for the interruption and for the delay. And once again.
You can start sharing your screen.
Okay. Can I able to see, ma'am? My screen is audible, visible?
Yeah. It's visible.
Okay, ma'am. Thank you, madam.
Vaitishwaran? Hello.
Yes, ma'am. Yes, ma'am. There is an issue in my network, ma'am. I think so. Can I present at the last, ma'am? Sorry for the interruption.
Okay. Now it's visible.
Okay, madam.
Move ahead, like quickly.
Okay, madam. Madam, I have very. Okay, madam. Good afternoon to everyone. Sorry for the delay and the interruption. I'm Vaitishwaran from the Kalasana University. We are presenting a computational investigation of the aerodynamic characteristics of a trailing edge serrated wing. And we are using here a NACA airfoil 4415. It has been chosen as a test model in the present of the study due to its widespread and real-time application. And NACA 4415 airfoil has been numerically investigated to the comprehend the flow physics related to the progression of the flow preparation and the variation in test unit parameters like lift, drag, and the surface pressure distribution. In most of the trailing edge serration, papers, they are studied aeroacoustically, but here we have studied the aerodynamic effect of the trailing edge serration. The computational fluid dynamics is the science of the prediction to heat transfer, mass transfer, and the related phenomenon by solving the mathematical equation which governs these processes using the numerical process. Here we use the Gambit software as in modeling, and measuring we use the Gambit and the ANSYS software, and the Fluent and ANSYS used for the flowing solver equation. These are the problems with flow separation occurred when the flow separation. The flow over the airfoil needs to be attached over the air. Take an inlet for an velocity invert and a pressure outlet as an outlet and the symmetry as a side and an wall for an airfoil wing section for the fixed wing. The above shown the figure or the two different diagrams. The left side we are seeing the baseline diagram of the airfoil that we made on the Gambit, and the right side we described the modified serrated wing we have drawn from the Gambit software. These shows the 6 graphs of the contour baseline wing diagram of an airfoil. The first diagram explains about the airfoil angle of attack at the 0 degree, and the second explains about the 5 degree decreasation, and the third describes about the 10 degree angle of attack differentiation, and the fourth, and the 15 degree angle, and the fifth explains about the 20 degree, and the sixth explains the 25 degree. These are the pressure contours of an aerodynamical optimum. We take amplitude at the 0.025 and the wavelength at 0.125. The graph shows the CL of our result. The graph illustrates that the variation of a coefficient of the lift, which is the angle of attack, for the baseline and the trailing edge serrated model from 0 to 30 degree in an increment of 5 degree. The variation of the CL, which is the alpha, has been discussed for the baseline and the 3 modified featuring cases. Trailing edge serration with the amplitude of 0.025 and the wavelength of 0.125, 0.25, and 0.5. From these graphs, that the lift curve characteristics of the trailing edge serrated wing model is differentiated from the baseline model. The lift curve characteristic clearly declines that the modified trailing edge serrated model shows better lift than the characteristic of the freestyle region compared to the normal baseline model. The CD graph. The CD graph illustrates the variation of the coefficient of the drag, which is the angle of attack for the baseline and the trailing edge serrated model from the 0 degree to the 30 degree increment of an 5 degree. From the figure, it becomes clear that the characteristic remains of the flow sheet apparently due to the influence of the trailing edge serrations. The coefficient of the drag of the baseline airfoil is relatively higher than the modified trailing edge serrated model. It is clearly evident from the figure that the greater angle of attack, the phenomenon becomes really visible. The determinants of computation model. The modified models are compared with the baseline model in order to find out the optimum model. The lift by drag ratio, which is the angle of attack graphs, are plotted and listed above. The models with the optimum air acoustic characteristics also defined with the help of the graphs plotted between the SPL and the DBL alpha for the baseline and the modified edge of the different value separations. This is the difference between the CL and the CD graph and the baseline of the all models. It excludes the variation of the coefficient of the difference between the coefficient of the lift and the coefficient of the drag of the all serrated model. Conclusion: a computational investigation have been performed over the baseline and the modified edge serrated wing and the future 3 different wavelengths of 0.125 and 0.25 and 0.5, keeping the amplitude at the constant of 0.5. Based on the numerical investigation, the following conclusion was made as follows. That's it, ma'am. The paper studied examples finds the broadband noise reduction of a linear cascade with the trailing edge serration. And on the mechanism of the serrated airfoil trailing edge noise reduction, the trailing edge reduction effect of the flap angle and acoustics. Thank you.
Thank you.
Hello. Thank you, Vaiteshwaran. Thank you for your fascinating presentation and best
thank you,
wishes for your future work.
Thank you,
Now,
ma'am.
question answer round is open. So everyone is welcome for the questions. It is for 10 minutes as we are running out of time. If any questions are there, then please come forward.
My question, I have one question. Hello, I am Ashok Kumar.
Yes, sir.
To Mr. Jadaveda, not to you.
Yes, sir.
Mr. Jadaveda, you have studied angle of attack. Again, a clarificatory question. That
Yes,
is, you studied the angle of attack from -5 to 20 degrees.
Yes, sir.
RLV. So are we not using the aerodynamic braking?
Not that way, sir. We'll be using both the elevon and rudder as the requirement maybe for controls. But the overall parameters of bringing it down would be, one is we need to also compensate for the lift under these circumstances.
Oh,
so it's a combination of how much we build up the alpha and use the control surfaces for keeping it at a certain path as we land out. So this being an unpowered system, we need to sort of glide down and unpowered using the aerodynamic parameters itself. So it's actually a combination of all of this which decides us to hold on to a trajectory for a particular point for us to come down while we are re-entering now.
I understand you studied for Mach 0.3 where control surfaces will be active. I understand that.
Yes, sir.
I know. But before, I'm just asking for clarification, my own understanding. Before that, higher Mach numbers, are we going for aerodynamic braking? How do we reduce the speed?
Sir, one is as we come down, so at much higher Mach numbers, we won't have much. Suppose I take it from re-entry point of view. As we start, we'll have a very rarefied atmosphere. So there, we're not sure to what extent it will be valid because the density is being very low. But as we come down, the aerodynamic parameters do definitely play a role, and then we're using all this. That is basically alpha buildup we'll do, and then use this rudders and elevons for breaking it down. That is breaking the speed down, bringing the speed down.
Okay.
Hello, do we have any other questions? Or can we move ahead for the next session? Dinesh, are you there?
Yes, Radhika. Do we have a tea break or can we continue?
Has session chair for the next session joined?
Yes, I'm available.
Can we proceed?
Yeah, please go.
Yes, Dinesh, continue.
Good afternoon, everyone. Welcome you all to the technical session 2 Propulsion. The chairperson is Mr. Sumit Kinvasara, an engineer by profession, a founder of Geospatial Design Lab. Within the last decade, have nurtured this organization to become one of the leading product and service providers in geospatial domain using remote sensing and GIS technology.
They are the major players in aviation in India and Middle East. Business apart, he deeply involved in activities of Institute of Engineers and Nasik Management Association. Currently, he is the chairman of Institute of Engineers, Nasik, also the president of Nasik Management Association. We welcome you, sir. If you wish,
Thank you very much.
you can have few words here.
Yeah, thank you very much for having me as a chairperson for the session. And it seems to be a very in-depth effort put in by the whole team from the IEI as well as those who are going to present for the entire session. So I wish you all the best for your session, and I would request you to please go as per the order.
Okay, sir. Thank you, sir. So with your permission, we can start this session with the first speaker from LPSC team. Modeling of fluid transit in propellant feed system using method of characteristics by Saurabh, Deepak, Rechi Joseph, Vijay Kumar, Liquid Propulsion System Center, ISRO, Thiruvananthapuram.
Okay. Good evening to chairman and all members. My voice is audible and the presentation is visible at all stations, I hope. My voice is audible and the presentation is visible at all stations?
Yes, sir. Yes, sir. Please continue, sir.
Yeah. So I'll be presenting on modeling of fluid transients in propellant feed systems using method of characteristics. I'm Saurabh Karmarkar, and along with me, Deepak, Dr. Rechi Joseph, and Mr. Vijay Kumar is joining from LPSC. We will be covering the presentation in this heading. We'll start with the introduction, a summary of literature survey, system description, governing equation, methodology used for solution, boundary conditions, and results. And we'll present the conclusion. In the liquid propellant stage, the fluid transients often occur during the starting and the shutdown of the engine. So the liquid propellant is stored in a propellant tank, which is feeding the liquid propellant to the engine through a system of feed line. And in this system of feed line, we have different bends, bellows, and the control components, mainly the isolation valve, which are dynamic elements, which are open or closed during engine start or shutdown process. This opening and closing of the valves creates a sudden change in the momentum of the fluid. This, along with the compressibility due to the compressibility of the fluid and the elasticity of the pipe material, causes a transient pressure surge, which propagates in the entire feed system. The surge pressure can happen either during the opening of during the engine start, mainly because when the valve is open, the propellant gushes out of the feed line and it impacts on the stationary impeller of the pump, which creates a surge. Or it can happen during the shutdown of the engine, where a feed line flowing full with the liquid is subjected to a valve closure and reduction in the flow rate. So then normally the experimental verification is only possible with a stage level hot test. And so an analytical estimation is presented here to estimate the design pressure for these elements. So to conduct a mechanical design of all the feed system elements, we need to estimate what is the maximum pressure required for which they have to design and qualify. And in case any analytical method is not available, we'll have to wait for a stage level test to complete. So using this analytical model, the surge pressure can be predicted beforehand, and the test requirement on the stage level can be reduced, thus expediting the development process. Normally, the prediction of this surge pressure during the fluid is done in many other engineering applications, like in hydraulic power plants, in gas pipelines, cryogenic transfer line, etc. And commonly used analytical methods for estimating the surge pressure is solving the governing equation, which is basically the mass and momentum conservation equations, using the method of characteristics. There are other methods also to solve this governing equation, like implicit finite difference methods, which are unconditionally stable and can handle complex fluid networks. However, it has some complexities which are as it involves solving couple set of linear and nonlinear equations, and the application of boundary condition requires some fictitious grid points beyond the flow domain. So for engineering application for estimating the fluid the pressure surge in the transient fluid network, the method of characteristics is commonly used. There is another model like liquid column model, which is mainly used for priming and line filling process. Then that is when a line is initially empty and it is primed with a fluid in a very short time, that also generates some pressure surge. So there is a liquid column model which can be used for that. So this liquid column model is used in past for predicting the pressure surge in spacecraft feed system, which are basically pressure fed engines. So in this work, we are presenting a method for estimating the surge pressure for a pump fed engine, where the pump dynamics play a role in the generation of surge pressure both during the starting as well as during the shutdown. And we also present a liquid column model coupled with MOC based method for estimating the surge pressure during the opening water hammer. This is a system which under our consideration. We have a propellant tank, the outlet of which is connected through a network of feed lines to the inlet at the inlet of the engine, which is basically a pump. And in between, we are having an isolation valve, which is opened and closed during the start and shutdown of the engine. So there are two cases which arise here. One is the downstream segment of the isolation valve. Either it can be evacuated and primed with propellant. In such a case, the closing water hammer is more severe, and the analysis focused to estimate the closing water hammer. In another case, when the downstream line of this isolation valve is not filled with the propellant, we are more interested in know the opening water hammer. That is when the line is getting filled by the propellant in a very short time, and the liquid front is getting impact on the pump impeller. What is a water hammer? That is another problem. In this work, we are mainly focusing on the closing water hammer case, where the surge pressure during the engine shutdown transient is analyzed for two cases. That is one engine shutdown case where the shutdown is governed by the valve closing as well as pump rundown, and second shutdown case where the only pump rundown governs the engine shutdown transients, and hence the surge generated. So the governing equation what we use here is presented. Basically, the conservation of mass and momentum, these two are the main equations, where we applied for a variable area control volume. So the short derivation is shown here. This is a variable area control volume, and we have different variables at each end. This is a 1D model only. So we are considering the variations only in one direction, that is along the axis of the pipe. And the mass balance, that is the force balance at the inlet and outlet, when equated with the mass into acceleration, Newton's second law, gives us the L1, that is the momentum equation for this flow. Here, variable area control volume is specifically chosen because during this water hammer phenomena, there is a dilation of the pipeline due to this elasticity, and that has to be accounted while calculating the surge pressure. Second is the equation of continuity, where we are simply equating the mass at the inlet, difference at the mass flow at inlet and outlet with the net mass accumulation inside the control volume, and that gives us this L2 equation. In the second equation, the continuity equation, the term dA by dt is basically related to the elasticity of pipe material, which is derived from the Hooke's stress formula. And the second term, the d rho by dt, is defined by the compressibility of liquid. So which is defined with as a ratio of based on the bulk modulus K. And substituting these two in the continuity equation and then doing some rearrangements by substituting this A square, which is the acoustic velocity given by this expression, we get a continuity equation which resembles with the wave equation. So now this L1 and L2 are the governing equations which are to be solved to obtain the pressure and the velocity field, that is pressure as a function of display as a function of local coordinate and the time, and velocity as a function of x and t. So we use the method of characteristics here, where the continuity and momentum equations are combined with a known multiplier, with an unknown multiplier, and we form a set of ordinary differential equation using this approach. So here we write L equal to L1 plus L2 and derive this equation. Now here we make an assumption that we make a substitution, in fact, that this lambda into rho a square, which is lambda is a multiplier in the first parenthesis, and in the second parenthesis 1 by rho lambda, these two are equal to dx by dt. By making this substitution, this converts into an ordinary differential equation which can be integrated over time to get the velocity and pressure at different time instances. But this substitution is applicable only along this characteristic curve dx by dt equals to plus minus a. So finally we have an ordinary differential equation which is applicable only along this characteristic curve. And if the initial values, that is the pressure and velocity at point A and B, if it is known, the pressure and velocity at point P can be calculated based on the previously known values. So this method, this equation is given by C plus and C minus equation. So C plus is characteristic equation with the plus sign, and C minus is the characteristic equation minus sign. Here we are replacing the velocity and pressure with the equivalent head and flow rate for convenience of calculations. Because in actual calculations, the flow rate is something which is measured directly from the test. Then coming to the boundary condition, for the closing water hammer case, only 3 types of boundary conditions we are having. That one is a tank upstream boundary condition, that is at the first end of the first node of the feed line, which is connected to the tank bottom. The reservoir head is constant, so we substitute the head at the first node as a given constant number which is known. And second, we use the C minus equation to arrive at the head at the downstream node. So using these two, we can calculate the pressure variation at the boundary node using these two equations. Then second boundary condition is valve inline boundary condition. So that is if we have a pipeline, and inside that we are having a valve which is opening and closing, and its opening closing flow rate is governed by the CDA relation given here. Here 3 unknowns are there. One is the head at the node N and 1. So the N node is the last node of the first segment, and 1 is the first node of the second segment. So here 2 segments are there. One is the upstream of the valve and one is downstream of the valve. Here we are the flow rate at the nth node and first node will be equal, because to ensure the continuity. So based on that, we write this equation for the flow rate. And C plus and C minus equation for individual segments is written according to the method of characteristics. So these 3 equations we can solve to derive the head and velocity at these 2 nodes. Then third condition is sudden bend, sudden contraction, expansion, and bend in the feed line. So as such, there is no separate boundary condition applied for that. The variable, the valve inline boundary condition itself is modified to accommodate these bends and sudden expansion contraction. So the pressure drop created by the bends and sudden contraction expansion is converted into equivalent effective CD, and this CD is used in the valve inline boundary condition. So these 3 boundary conditions are normally we have used for the closing water hammer. In case of opening water hammer, there are another 2 boundary conditions which get added over this. First is the constant flow rate at the end of the pipe. So if we are going for a line filling or the transient pressure surge during the opening, the flow rate at the last node has to be previously defined, and that is known. And second, the head at the last node is given by the C plus equation. So this is an analogous to the constant head boundary condition in the reservoir. The second is line filling downstream of the valve using liquid column model. So the second segment downstream of the valve here is not discretized. Here it is only solved using a force balance of the liquid column. So basically the inertia of the fluid, that is rho ax dx by dt, is equated with the forces acting in the on this fluid element. So the forces acting are the pressure forces on the upstream and downstream, and the friction forces on this element. So based on that, we arrive at a force balance equation for this fluid element. Then other equation is the C plus equation for finding the head. And again, we incorporate the condition that the flow rate at the nth node and first node are equal, and is given by the CD relation for the valve. So these unknowns, that is the head at the nth node and first node, and the flow rate at these 2 nodes, are calculated by solving this equation. So using this model, we have computed the surge pressure for two different cases of closing water hammer. The one is the case where the closing water hammer is generated by valve closing and pump rundown. That is, the valve is also closed and the pump the pump power is also reducing simultaneously. So there are two effects here. In second case, only the surge pressure is only due to the pump rundown. That is only the reduction in the pump power is causing the reduction in the flow rate, and valve remains open here. So only one effect is there in the second case. So for the first case, the case is when the command for the engine shutdown is given, there is a reduction in the turbine output power because the gas generator regulators and valves are closed. This causes the pump speed to come down, which reduces the flow rate initially. So we get two pressure surges here. One is the initial surge due to the pump rundown, and second peak we get when the valve is getting closed. So we can see here the flow rate versus time curve is shown here. This is from the model prediction only. The flow rate initially drops because of the reduction in pump power, and after 1.25 seconds there is sudden reduction in the flow rate, which is mainly because of the valve closing. So we see that the surge due to valve closing is having higher magnitude than the previous one. This result of the pressure surge, what I am showing here, is model prediction compared against the pressure measured in the stage level hot test. So we can see the model prediction is closely matching with the pressure what we have experienced in the stage level hot test during the closing engine shutdown condition. The next case is the surge due to the pump rundown. So here, these results I'm showing for another case where the engine transients are different than the previous one, and the flow rate reduction is caused only due to the drop in the pump or turbine output power. So the flow rate transients are given here, what is given as an input in this particular case. As we can see, the flow rate reduction is very drastic. In 200 milliseconds, the flow rate reduces from full to around 10%, less than 5%. And because of this drastic fall, we see that the peak pressure here is more than the peak pressure what we have seen in the previous case. Also, the pressure at two different stations are shown here. One is at the isolation valve inlet, and one is at the feed line elbow. So the feed line elbow is somewhere around 4 meter higher elevation than the isolation valve inlet. So we see that there is a significant damping of pressure wave as in the upstream of the feed line. And this damping is consistent for the previous cases also. So to conclude, a mathematical model for estimating the transient pressure surge in the fluid network with multiple fluid system components in line is generated. And the modeling framework developed here is very useful for estimating the transient pressure surge for given system parameters and engine transient. We could in fact avoid some number of tests which were required to do to arrive at design pressure, and it also expedites the design process of the system. And these predictions are validated from the test result from a ground test of a liquid stage, which was previously tested which is having a different configuration, but we have validated our result with that configuration only. And this was fully utilized to define the design pressure of feed system elements, and also to study the parametric effect of engine variables on peak pressure, peak surge pressure. That is, if we change the response time of the valves, what kind of pressure surge we are getting, all those things were properly studied. Further to this, a liquid column model for integrating with MOC is developed, and it is proposed, which can be used for estimating the surge pressure during priming and engine start. So far, we have seen that the liquid column method, liquid column model with MOC is used only for the spacecraft kind of application where pump-fed engines are not there. It's a pressure-fed engine, but we can develop it for a pump-fed engine also, which we have shown here. So finally, this modeling approach and the code developed here can be used for analyzing the transient pressure surge in other engineering systems also, like in hydraulic power plants, in civil water distribution system, and gas pipeline network analysis, etc. So this is all from my side. Thank you for your patience listening. Thanks.
Thank you, sir. Thank you for a very insightful presentation. So anybody have any doubt regarding these presentations or open? So if there is no doubt, so we can go with the second presentation. Mixing enhancement of secondary jet using a curved pylon in supersonic flow by Anbarasan Sekhar and Professor Aravind Vaidyanathan, Department of Aerospace Engineering, Institute IAST, Trivandrum, Kerala. So, anybody here? Anbarasan Sekhar? I think they are not here. So can we go with the third presentation? Swaroop, can we go with third? Swaroop, not. Reggie Joseph, can we go with the third presentation? LPSCT.
Sir, am I audible now?
Yeah.
Yes, sir. I'll share the screen.
Okay. Thank you. So third presentation is challenges in design and testing of liquid booster stage propellant tanks by Deepak, Suresh, Reggie Joseph, and Jagannathan, LPSC team, ISRO, Trivandrum.
Yes, sir. Is the presentation visible, sir?
No, sir. No. Yes, sir. Yes, sir. You can start.
Good evening, sir. This presentation is regarding challenges in design and testing of liquid booster stage propellant tanks. So this is an overview of the presentation. First is an introduction about design of propellant tanks, then the design process, how that is done, then the various challenges that are encountered in design and testing, then a brief review is mentioned about the test results, then qualification test is covered, and then conclusion. So coming to the introduction, launch vehicles have multiple stages designed to achieve diversified mission requirements. So in a multi-stage launch vehicle, based on the propellant that is used, it can be classified as solid propellant stage, liquid propellant stage, and hybrid propellant stage. So in a solid propellant stage, both the fuel as well as oxidizer are in solid state, whereas in liquid propellant stage, the fuel as well as oxidizer both are in liquid form. In hybrid, one of the either the fuel or the oxidizer is solid, whereas the other is liquid. So in a liquid propellant stage, based on the temperature of the propellant that is stored, it is classified as earth storable, wherein both the fuel and oxidizer are at ambient temperature. Semi-cryogenic, wherein either the fuel or oxidizer is at cryogenic temperature and the other is at ambient temperature. And cryogenic, where both the fuel as well as oxidizer are in cryogenic temperature. So this coming to the GSLV Mark III vehicle configuration. Here, there's a strap-on stage, which is a solid stage. Then there is a liquid booster stage, and on top of that, there is a cryogenic upper stage. And here, there's a payload coming, which is encapsulated in an assembly, which is covered with a payload fairing. So here, in this case, this is a okay, this can either be a semi-cryogenic stage or a storable stage, whereas this is a cryogenic stage. So booster stage actually carries the mass of the that is upper stage as well as the payload that is coming on top of it. So it needs to have a higher density impulse. So and then liquid propellant stages are widely used for vital mission controllability, high specific impulse, easiness in operation, non-hazardous, and it is safe as well. Then coming to the design cycle flow diagram for propellant tanks, this is the general cycle a flow chart that is followed for the design and acceptance testing. So here basically we require inputs, initial inputs like geometrical detail, structural interfaces. What are the mountings that are coming? Then the raw materials. Based on that, a preliminary configuration is arrived at, and then considering the pressure and structural details, as tank domes as well as shells are the sizing of that is done. Then this is taken for an analysis, a detailed FE analysis, and based on this FE analysis, the design is optimized, and the critical load cases that are required for testing are identified. So based on this optimized design, a proto hardware is realized, and then the closure as well as the test interfaces. What are the interfaces required for pressurization, venting, and fluid servicing? Those are realized. And then this proto hardware is initially subject to qualification testing to validate the design methodology. So for that, this test setup was erected, then instrumentation is carried out. Before this qualification testing, leak check is done. If that is acceptable, then it undergoes production batch, realization of production batch and acceptance testing. Otherwise, the design modification, it is an iterative process. So coming to the propellant tanks design inputs. So here you can see semi-cryogenic stage is these are the tanks over here. So the mass of the tanks will add to the inert mass of the stage. So this has to be the mass of the tanks, propellant tanks have to be minimized. But then that is done after a trade-off study between different design choices. So various design choices are given here. That is the geometry, what is the vehicle geometry. Based on that, the tank geometry is identified. Then the materials, what is the materials that can be used for fabricating the tank. That is considering the propellant compatibility and operating conditions. Then the functional interfaces, whether it should be a searing joint or o-ring joint. Then the mechanical interfaces, what are the additional structures that are coming, which are getting attached to this the tank. Then the raw material size and the fabrication techniques that are available. So based on this, a trade-off study is done and the final design is arrived at. Then these are the design options. First is the geometry, that is optimum shape of propellant tank is spherical because it gives the least weight for a given volume. But in our case, cylindrical tank with spherical end domes are commonly used because considering the space constraint and mounting difficulties of spherical tanks. Then the materials, composite materials offers less mass and it has limited availability. And it has higher cost also. And the fabrication process involved is very complicated. So aluminum is widely accepted as a better choice among all the materials. So if you see a propellant tank, a typical propellant tank drawing here, this is a 7-meter tank. So while designing and testing, so many challenges are encountered. So major challenges that are encountered are mentioned here. One is finalizing the tank ullage pressure, identifying the raw material for fabrication, mass optimization. Then the material used is aluminum A2219 alloy, so it has a comparatively low weld strength. So how that is that challenge is overcome. Then identification of critical load cases. Those are the design challenges. Then coming to testing, simulating the test, that is erecting the test setup and conducting the load cases that are coming on this tank. That is one challenge. Then achieving the required leak tightness in the various openings, various joints. Then LN2 servicing of cryogenic tanks to simulate low temperature. Then limited availability of costly feed-through connectors. Coming to the ullage pressure requirement, that is one of the challenges in design. This ullage pressure is given by this equation over here. That is it arrived at considering the net positive suction head, the vapor pressure, the friction losses in the feed line, then the elevation head. So considering this, on top of this, the tank dilation, that is in case a strap-on motor is acting during the operating regime of the stage, then a tank gets dilated. So there will be a pressure drop. In addition to that, once the engine is ignited, then the propellant starts flowing to the feed line, the engine. That time there is a pressure drop, and because of the delay in response of the pressurization system, that also needs to be accounted for in this ullage pressure. Then on top of that, the dispersion on regulated pressure. So all this and sufficient margin should also be added to this. So this at various instances of this flight, this is the acceleration profile, in fact. So based on this, the NP, the alleged pressure will vary. So alleged pressure, that is whatever alleged pressure that is obtained at various instances, that acceleration head is added to that acceleration head at the aft and dome of the tank. That is added to this alleged pressure to obtain the MUP. Then coming to the material selection, here, okay, the selection parameters are high strength to weight ratio. Then the propellant should be compatible with the pressure. The material should be compatible with the propellant as well as the pressure. Then it should have high fracture toughness, ductility at operating temperatures, at operating conditions. Then it should be resistant to stress corrosion cracking. Then it should there should be easiness in fabrication, and the material should be readily available. So considering various parameters, for our case, we have chosen aluminum 2219, which is an aluminum copper alloy, which is resistant to stress corrosion, and it is widely available and with low cost. Earlier in launch vehicles, we were using 7020, which is an aluminum zinc and magnesium alloy, which is having weld efficiency of over 90%. But then this was also readily available and the cost was also low. But then it was susceptible to stress corrosion cracking. So we are presently going for this AA2219. And these are the material properties of 2219 alloy. This at RT, the YS is 350 for in temper condition T87. For T851, it is 276. Then another challenge is UTS-based design philosophy. Here, this is a mass optimization technique. In this case, local yielding is allowed at geometric discontinuities and well locations, but global yielding of the tank is not allowed. Whereas in ultimate load conditions, the stress should be within the design strength. So these are the typical loads that are acting on the tank: the tensile load, compressive load, bending moment, and other loads. So based on the from the lift off to the burnout of the stage, we will be considering various at various instances what are the loads that are acting, and then the critical load cases from those number of loads that loads we'll be identifying critical load cases, and these critical load cases will be taken for testing. Then the problem with A2219 is that it has low weld efficiency. So that is around 50% of the parent material. So that is overcome by increasing the thickness of the material near the weld, and subsequently that thickness is reduced to the parent material thickness. So that that is done after several iterations, and considering a lot of mass implication study is done, and based on that, this land width as well as the weld steps, the thickness steps, the step thicknesses are arrived at. Then these are the general testing criteria. For acceptance testing, the pressure will be 1.1 times of the MUP. Then structural load will be 1.1 times of the flight expected loads. Then qualification test pressure will be greater than or equal to 1.25 times of the MUP. Then structural load also will be 1.25 times. The factor taken is 1.25. Then the acceptance criteria is that we'll be instrumenting with various strain gauges. So the strain gauge value should be within 7,000 microstrain to 10,000 microstrain. Then the leak rate should be less than 10⁻⁻⁴ standard cubic centimeter per second for removable flange interfaces, and 10⁻⁻⁷ should be less than 10⁻⁷ SCC per second for weld joints. Then structural qualification is done. The critical load cases are identified, and structural qualification for any new hardware is done. That is to validate the design and analysis methodology and to compare with the theoretical estimates. Then this is carried out for every hardware before regular production. The critically stressed location and the local behavior of joints, the structural interfaces which were not fully simulated during the analysis, that can also be captured during this test. The deformation of the tank during the actual loading, it can also be estimated. This is this can be classified into a structural qualification load test and ultimate pressure test. In this qualification load test, the tank is mounted with adjoining structures to simulate the interfaces as in flight condition. For cryogenic tanks, that will be tested with LN2, liquid nitrogen, to simulate the thermal stresses at actual operating temperature. Then for ultimate test, the tank is pressurized. There will be no load applied, only pressure will be applied. That is 1.25 times of the maximum expected operating pressure. at RT. This for cryogenic tanks, correction factor, environment correction factor will be applied, and this test will be done at RT. Then the acceptance criteria is that the tank and interface joints it shall withstand the ultimate loads without failure. This is the typical load setup for this conducting qualification testing of the tank. This is the tank over which adjacent structures are assembled, and then the loads, various loads, the critical loads are applied using these loading jacks, 16-point loading jacks. Before the test, actually the tank is prepared and various non-destructive testings are done. Then the instrumentation is done to capture the strain gauges, the displacement, and then okay, the structural testing during this testing, the tensile compressive loads, variable axial loads, then shear force, bending moment, everything is the loads are applied. And then after the test, the assessment of test data with predictions that is done. The test data is analyzed and non-destructive testing is carried out. Then acceptance, coming to acceptance testing, all tanks once it is under regular production, those are acceptance tested. All this acceptance test is done at RT, because the even for cryogenic at cryogenic temperature the properties will only improve. So it is better to do a testing at RT. That this is done to verify that the materials, manufacturing process, workmanship, everything meet the specification, and to ensure that this hardware is suitable for flight. So in that can be classified as proof pressure test, wherein the proof factor of 1.1 is applied, and 1.1 is multiplied with the MUP, and that pressure is applied. Then for acceptance load testing, again, if that in some cases the simulation of critical structural load, that is through pressure alone, if it is impossible to capture that, then load also is applied. Then the challenges encountered in PPT is that PPT should be conducted with a pneumatic medium, because hydraulic medium wetting could lead to corrosion. Then for that, specifically built facilities will be required with adequate safety precautions. That is used for conducting tank PPT. So the PPT is done by placing the tank in a horizontally mounted condition, and then instrumentation, extensive instrumentation, LVDT, strain gauges are instrumented on that for assessing the tank behavior. Then the results, the design of enclosures of the tank openings. That is, the tank will be having various openings. So those during the test, it will be kept closed. So these closures require there should be a better leak rate. Leak tightness should be there for this closure. So that is one of the challenges that is faced. So achieving a leak tight closure. The tank is acceptance tested at 0.734 MPa, and pre and post leak checks are done at all well locations and nozzle joints. So these are the results at before PPT. That's better than this for flange joint. That is better than 10⁻⁻⁴ SCC per second. After PPT also these are the values. Now further tests are planned. That is the structural test with LN2 for cryogenic tank, and then ultimate pressure of the tank. So concluding the complexities and challenges in design of a propellant tank for liquid booster stage, 4-meter class liquid booster stage, that is covered, and phases of qualification, testing, and acceptance are identified. The design is evolved in a systematic process considering all influencing parameters. Propellant tank design is a trade-off between mass control and design margins. The realize the tank and validate the process identified to achieve the temper conditions. The non-conventional interface closures simulating the operating stress levels and incorporating interfaces for fluid servicing as well as instrumentation, that is design. Then test metrics is evolved encompassing all the load conditions, and tests are in progress. Proof pressure test is carried out, and this meets all the test conditions. Further tests like structural load test at 77 Kelvin, that is LN2. Then ultimate pressure test and margin evaluation is in progress. These are the references. That's all from my side.
Thank you, sir. Thank you for the wonderful presentation. Anyone have a doubt? Is available. So we can go with the last presentation. Effect of jet to cross flow momentum flux ratio on flow characteristics of hydrogen jet in supersonic cross flow by Imran, IIT Kanpur, and DP Mishra, chairman of National Institute of Technical Teacher Training and Research, Kolkata.
Hello, sir. Am I audible?
Yeah, you're audible. You're audible. Please go ahead.
Okay. Okay. First of all, thank you, Session Chair, for giving me the opportunity to present in this conference. And my name is Imran Rashid. I am from IIT Kanpur, and my teacher supervisor is Professor Prasad Mishra. So today I'll be presenting effect of jet to free stream momentum flux ratio on the characteristic of a hydrogen jet in supersonic cross flow. So the overview of the slide will be like introduction, then objective of the study, then we'll move to computation details, then validation of the solver, and we move on to results and then on to the conclusion part. So in today's world, actually, for military as well as civilian applications, we are looking for faster modes of travel. And the current problem with low speed propulsion system is that when it is going to be used for high speed propulsion, there will be increasing structural and thermal loads due to the material limitations. So what happens is, in that case, we have to go for a propulsion system without any moving parts, such as ramjet and scramjet. Now, the problem with the ramjet, both uses ram effect for compression of the incoming air, and further it is further it is given to the combustion chamber. In the case of a ramjet, the incoming free stream is slowed down to subsonic speed, and then combustion is happened in the combustion chamber. But what happens is, at higher Mach number, for example, at around Mach number 6, the pressure losses due to this ram effect, is due to the slowing down of air, will cause more pressure losses. So we need to carry out the combustion in the supersonic free stream itself. Then comes the concept of a scramjet combustion. But the main difficulties for these type of combustion system is the first one is the design challenges, because the condition at the combustion chamber should be proper, and in order to do that, your diffuser section should be the design of the diffuser section should be such that a proper formation of the shock trail should be happening in the diffuser section and the isolator section. And another problem is the operating challenges. It cannot be start from the zero. Then we have material limitation, and further when it comes to combustion, there are challenges according to combustion also. For example, the residence time of the fuel is very less in this case, so we have to ignite the fuel in those short residence time, and cooling which is needed for the combustion chamber walls and the nozzle walls is also another issue. So first of all, we'll summarize about what types of injectors are we using in a supersonic combustion cases. There are two types. First is intrusive and non-intrusive. Intrusive means we are directly putting some structures in the flow field, such as track, ramp, or pylon. And then we are injecting the fuel. And what happens with this is, there is a physical obstruction in the flow field, but it will help for better mixing of fuel and free stream. Then we have non-intrusive techniques such as cavity, transverse injection, and multi-stage injection. Here there is no physical disturbance in the flow field, but we can also achieve sufficient level of mixing and combustion with these types of injectors also. And in this presentation, I'll be talking mostly about the transverse injection part. So in a jet in supersonic cross flow, there are some structures which are common in most of the configuration. For example, the formation of a bow shock, a counter-rotating vortices, then horseshoe vortices, then wake vortices. These are all common in most of the flow fields actually. So in the present study, I am investigating the effect of jet to free stream momentum flux ratio on the performance of a jet in supersonic cross flow. And here J is defined as the ratio of momentum of the fuel to that of the incoming cross flow. So these are the computational details. And this is our computational domain and the boundary conditions. Here we have air inlet. We will give pressure, temperature, and velocity as this point. And the upper boundary is treated as symmetry. And we have an isothermal flat plate. And we have fuel injector also. And the flat plate is at 300 Kelvin. And both the lateral boundaries are also at the symmetry conditions. And we are investigating 3 different values of J, 0.71, 2.71, and 5. The condition corresponding to that are given in this table. And air, we are giving a 2.4 Mach number at 1400 Kelvin. And the study is 3D unsteady RANs and modified reactor. Hello? Hello, am I audible?
Yes, sir, you are audible. Please continue.
Okay. So for the present study, we were using open form package and the pro-central form solver, which is initially for high-speed non-reacting flow, is actually modified to accommodate the species transport also, and 3 levels of mesh resolution. And the Y plus near the flat plate is actually less than 1. And SST K omega model is used in the present study. And for post-processing, we use ParaView and TechPlot. So for the validation, we use velocity at two different streamwise location for a similar configuration, where the similar configuration experiment done by Santiago and Dutton. Here both the working fluids, both the jet and cross flow are air, and D is equal to 4 mm, and the J was at 1.73, and the Mach number is 1.6. For 3 different mesh resolution, we first investigated an experimental study by Santiago and Dutton, and for 2 different streamwise location along the jet center line, we validated the streamwise velocity. And we can see that for 3 levels of mesh configuration, the solver is capable of predicting the velocity flow field in a non-reacting flow to a great extent. And moving on to our result, in our case, we will be studying a hydrogen jet in supersonic cross flow. So in order to validate the 3 mesh resolution which we took, we compared the J is equal to 5 jet penetration for 3 different mesh resolutions and validated the mesh size actually. And then we move on to comparison between 3 J cases for jet penetration. For the jet penetration for experimental studies in mostly are taken as the visible outer jet based on the flow visualizations. But for a numerical study, we have to rely on the mass fraction of the fuel. In the present case, we took the jet penetration height as height from the flat plate where the mass fraction reduces to 0.01 for all the cases. And here we compared 3 cases and we can easily see that for J is equal to 5, the penetration is much higher. And for J is equal to 0.071, penetration is less. So that means the penetration increases with increase in the momentum flux ratio because of the increase in the momentum of the jet. And then we move on to the mixing of jet and free stream. There are different parameters which we use for comparing the mixings of all the cases. One is the mixing efficiency, and second is the maximum fuel mass trajectory of the center line actually. So in the mixing efficiency part, how we do that is we take a cross section and we take the total mass flow of hydrogen present in that cross section, and we compare the mass fraction of hydrogen which is actually properly mixed, and that will give the ratio will give the mixing efficiency using this formula. Here we can see that the smaller value of J is performing better among all the three cases, and also the mixing efficiency is very steadily increasing. This is because since the momentum of the jet is very less, it is easily getting cleared by the incoming free stream. At the same time, for the other two cases, we compare J is equal to 0.71 and 0.5 at start near the injection area. The mixing efficiency is almost the same. Further, for J is equal to 2.71, it increases a little bit, but there is not much difference happening here. And by comparing the maximum fuel mass trajectory, it is seen that there is a sudden drop in the hydrogen mass fraction at the center line for J is equal to 0.7. This means that as soon as the jet enters the testing chamber or the combustion chamber, it is getting straight away deflected by the fuel, deflected by the air, and is getting cleared by the air, which result in a decrease in the mass fraction. For the other two cases, as expected, J is equal to 2.71 is decreasing fast. But at the end, for J is equal to 5 and J is equal to 2.71, a similar value of maximum mass fraction is observed. Also, we compared the mixing length. Mixing length means the distance from the injection to the any streamwise location where the maximum mass fraction reduces to 0.3. So as you can see that J is equal to 0.71 mixes fast. As a result, the core of the jet is breakdown fast enough, and at X by D is equal to 25, we were able to achieve 0.3 maximum mass fraction. At the same time, for the other two cases, the same mixing length, the same mass fraction was obtained at the end of the combustion chamber actually. Here we compare the mass fraction contour for three cases. This is J is equal to 0.71, B is equal to 2.71, and C is equal to 5. And here we can easily see the decrease in the mass fraction of fuel, which result in the higher mixing efficiency. For these two cases also, for J is equal to 2.71 and 5, at the end of the combustor, we see that the maximum mass fraction along the center line is almost similar. Here we can see almost the same, but at the same time, due to the action of the counter-rotating vortices, there are more fuel available at the both lateral sides of the J is equal to 5 case, which result in the lesser mixing efficiency than J is equal to 2.71. Now we move on to the total pressure loss. Total pressure loss can be defined as, here we use pressure loss ratio as the parameter for calculating the total pressure loss, which exactly is the available total pressure, which is the total pressure of the cross flow plus injected jet to that of the total pressure available in a cross section. And because of mixing and blockage of the flow, there will be obvious reduction in the total pressure at the cross section, and we are using this parameter to measure that. Now, higher the value of pi means we have higher pressure loss, and in the case of J is equal to 5, because the blockage of the cross flow by the jet is maximum at J is equal to 5, we have higher pressure loss at this case. followed by J is equal to 2.7 and 0.7. At the same time, near the injector, 2.71 and 0.7 does not differ much. But as we move along the streamwise direction, the pressure loss for J is equal to 2.71 is increasing. So concluding the study, we carried out 3D RAND study of three J values, 0.71, 2.7, and 5. And we observed penetration and how the mixing is varying and the total pressure loss for all the cases. And we saw that penetration is higher for higher momentum flux ratio, and mixing and total pressure loss is also higher for the higher momentum flux ratio due to increased blockage of incoming free stream, and the mixing efficiency actually decreases with increasing J, such that low value of J shows excellent near field mixing and also smaller mixing length. So we can conclude that increasing J did not result in better performance from a non-reacting perspective, and among the three cases study, 2.71 seems to be an optimum J value for the performance study conducted. That's all. Thank you.
Thank you, Imran. Thank you for the wonderful presentation. Any panelists have questions regarding this? Imran is here for you.
What can be the optimum gap between the injecting points? Have we looked into that?
Actually, sir, our next part of the study is exactly the same thing.
Okay.
We were actually trying to see gaps between the injector.
Okay. And injection pressure, effect of injection pressure?
Injection pressure is actually, when you look at the three different J cases, the one which we are varying is the injection pressure only.
To increase or decrease the mass?
Increase or decrease the mass flow rate and thereby the J values.
Then question is with regard to the size of the orifice.
Yes, sir.
What is that effect will be?
That effect actually, we didn't do the study for that yet, but we are planning to do in the near future. Because unless we studied about that, the effect of that orifice diameter, we cannot conclude like that.
Okay.
Another parameter which may come into picture is the injector variability. Whatever you make, the manufacturing variability of the injector also will come in.
Yeah, CVD effects.
Yeah.
Yes, sir. Question.
Okay, thank you.
Thank you.
Thank you, Imran. There is one more presentation. They are absent today, I think. Any questions regarding before presentations by LPSC?
Yeah, in fact, I have one or two doubts rather on the second presentation by LPSC. Deepak, are you there? Sir,
yeah.
Can I ask that question? That is, you said the qualification test is 1.2 times of MEOP and PPT is 1.1 times of MEOP. What is the criteria for selecting that numbers? That's first question. Second is, I will ask both questions. Second is have you ever looked into the stiffness effect of the closures on the stresses adjacent to the openings? These are the two questions.
Yeah, very nice, very valuable question. Yeah, first one I'll answer. That is, you are talking about the
1.25 into
I mean,
AOP.
yeah, margin. There is no definite criteria for any margin. So it's a design parameter which we say if you can have more margin, the problem is we will have more mass impact and it will be affecting the payload fraction. So normally in ground lower stages, so booster stages, we go for like margin of 0.1. It has to be, it can be a 0.05 also we practice for upper stages where we'll get more advantage of the mass. So it has to have a positive margin. That's all condition. Other things depends on the designer. Second factor is on that is on the acceptance test. Qualification test is whatever we have designed is design methodology itself. We are putting a factor of 1.25. So whether the design methodology is validated by means of a 1.25 factor, that will take care of all the uncertainties in the parameter like design parameters, material defects, all things will be covered by that. So 1.25, it will be going through the almost touching our design limits. So that 1.25 is generally followed everywhere. For acceptance testing, that margin will keep only between, it can be anything between any positive margin and any lower margin, lower advantage, any higher margin will have the mass impact, but we can be sure that your system will work properly. And the second question is on closure. Yeah, it's a very important thing. Actually, by putting a closure, we should not include we should not two conditions. One, either the nozzle should not be over tested. The same way, nozzle has to be undergo the pressure test also. Have the required stress levels also. So the closure also analyzed actually in the flight condition. Suppose if it is a welded joint, that welded joint condition, whatever stresses experienced by the our ring, nozzle ring, will be simulated by means of the closure. So that closure design will be decided such a way that it will be simulating that one. That is one of the main challenges. I think he has not highlighted properly that very valid question is done. It's analysis done with both condition and both are giving similar result only. We will proceed with the closure.
So closure itself is a design rather than a functional requirement. Okay, thank you.
Will you ever, Raji, will you ever go to bus test nowadays?
Yes, sir. Now we are planning. We have not gone any. Never we have tested that. This time we are planning because now we got the facility also. So that will give the exact margin what is available in that tank.
No, that will give a lot of relief to the manufacturing people like me, because if the first tank is having a lot of deviations, for first example, first tank is having a lot of deviations on the lower side, your acceptance test PPT you may qualify, you may qualify and you accept it. But in the qualification test, will you be having the sometimes when you do the qualification test, if the margins are, if the deviations are on the lower side, many combinations of deviations are on the lower side, like a well defect, so many things. It may burst also. Sometimes we don't know because we don't have the confidence, but it may withstand the qualification test. In that case, will you accept the design that with the deviation, or what will be your stand?
Sir, now we are going by the analysis.
The qualification test. It may withstand the qualification test, but with a lot of deviations. Will you accept the tank with the qualification test?
Provided, suppose some defect may be there in a non-critical area. Suppose one thickness has gone down. Assume that one thickness has gone down. Some area we have sufficient margin because we have kept uniform criteria for suppose dome. We have kept the same uniform. So that we can accept. But once you, as you told, once you have a burst test data and exact margin is available, then it will be decided to accept. It is easier to accept some more deviations, or we can take a decision very easily.
So I always prefer, that was my stand also long back when I was there. We have to conduct a burst test one time. Plus qualification separate. Actually, it should not be combined, in my opinion. Qualification should be separate, whatever you want. And burst test should be separate. If that is the case, lot of deviations, we need to again conduct any more tests and all. If you have the stress level, everything available in the bus test, You can straight away accept the deviations in case if it is happening, not that deliberately anybody is doing that.
Right, sir. So now it will go, as you told, first it will go PPT, then it will go structural test, then third it will go ultimate pressure test, then it will go for the burst test. All are different tests.
Yeah, you destroy one. That is actually that way we save a lot of time for the entire of the design for the entire period for many launch vehicles.
Right, sir. Yeah.
We will leave it to the designer probably. Thank you, Reggie.
Yeah, thank you.
Yeah, all the presentations were so good. Even the last one, I was with from NITTR also. I was closely watching. Very nice, new one actually, new area.
Yeah.
One, but the studies, as Ashok daily asked, there are a lot of things pending, but whatever we are doing itself is a new thing, no?
Yes.
Everything has to be slowly we can progress. Only we can progress.
Yeah, but I think that same team has to continue. I mean,
continue the effort.
Under the same professor, it has to
the
continue.
studies. That is more important actually.
Yeah. Actually, it is giving a lot of information or confidence to the system design.
Yeah.
Like, hydrogen is injected into the airflow for supersonic combustion. These are all very important data which can be used anytime. So all set of data, I think the same professor has to continue contributing to this study maybe by different students, but
the project should continue.
Professor should continue, and at the earliest it should be completed as well, because this is very emerging field. Supersonic combustion, scramjets, missiles, and mainly for missiles. We already have BrahMos, but then data generation is very important. So all the best for the professor. I don't know who he was. Okay.
BrahMos is now going hypersonic.
Hypersonic, yeah.
Okay, yeah. Thank you.
So are we winding up for the day?
Yes, sir. If there is no questions.
Decide to wind up. Okay. The chair can decide. The session chairman is there.
Mr.
Sumit sir.
Yes, I am here.
What is to be done further? Please advise.
We can.
Sir, so all the papers are presented, sir. May we conclude for the day, sir, with kind permission from all the chairs?
Yes, please.
Please declare that.
Okay, sir. May we conclude, sir?
Yeah, please.
Tomorrow our session will start by 10:30. Our third technical session will be there, sir.
No, today, one question I want to ask. Today, a lot of people who are presenting tomorrow were there in the audience or were there in the attendee list. Will they be coming in the panel list tomorrow? There will be a separate link for them for panelists.
No, sir. Same link they can join.
But
No
they'll
problem,
be panelists tomorrow. Is it like that?
No, sir. They can join from the same link, but keep themselves as mute and they can attend. No problem.
No, my question is, many of the tomorrow's presentations, people, today they are attendees. Today they are in the attendee list. Somebody called me and asked.
So attendee list, sir, they have joined from their respective.
Their worry is attendee will not be having a sharing right now.
Sir, actually what happened, if anybody joined from the registration link, then he will be the attendee, not panelist. For being a panelist, he have to only share for the link that has been forwarded to his respective email.
So all the authors are having a panelist link also, no?
Yes, sir. For all the authors.
Okay, please. So today we are making it clear that anybody who are tomorrow presenting has to log in.
Join from the link only.
They have been link only, not through the attendee link. Okay.
Not from the registration link. Only from the panelist link.
Okay.
Also, I request organizers to physically, personally verify with the presentation teams that they will be available tomorrow. Remind them. That will be good for our sessions. Otherwise, today IIST one team is not presenting. This can be avoided if possible.
Okay, sir. Okay.
Please try.
Kindly pursue with the others to make sure that tomorrow they are presenting. Okay, at least one call you can make and only some 10 papers tomorrow.
Yeah.
Okay. Make sure
Yes,
they are
sir.
coming tomorrow and presenting. That's all.
Okay, sir. We have not the phone number. However, we are sending
Or
one mail.
mail, or one mail you can send to
Okay, sir. Okay.
with the group mail for 10 people. The primary author, you can have the group mail for 10 people and send it to others tomorrow. And ask them to log in from the panelist link. Not
Panelist link only. Yes,
not
sir.
as a registered link. That also you make it clear, because many people are under that confusion today morning. Okay.
Yes, sir. Yes, sir.
Okay.
I'm sending one mail. Yes, sir.
Yeah. Thank you.
Okay.
Thank you, sir.
Thank you very
Thank you
much.
so much. Have a nice day. Okay. Thank you.
Similarly, that time limit also can be initially told.
Yeah. That
Today
also
late.
it's clearly, so that it will be on time, so that the validity, everything will be on time. Okay.
Yeah, that session chairs should take
Yeah.
care actually.
Okay. Yeah. We were lucky today that one paper was not there, otherwise it would have overshoot. Okay. Yeah. Thank you.
Thank you, sir.
So shall I leave then?
Yes, sir.
Okay.
We
Then.
are-
Thank you then. Yeah, fine.
I'm closing, sir. I'm closing.
Yeah. Okay, fine. Thank you.